All right, and also if you have questions and comments, we don't have to worry about passing around the mic. Apparently there's microphones in the ceiling, so if you have questions, you'll be able to talk and everyone should be able to hear you. I don't see them either. I see a few of you looking around. We'll figure this out.
They work.
They work. All right, that's good. All right, so why are we here? We've actually been seeing a lot of new SSD form factors, different thicknesses, concerns on where these form factors are going to go in the next few years. So hopefully getting us all together and going through some of the pros and cons of the new form factors that we see. Let's try to make these standards something that's going to live more than 1 or 2 generations, and that we don't run into problems like we've seen with form factors like M.2. So we'll cover that, but before we jump into the presentations and the technical data, let's actually talk about the survey. So I don't know if you actually had an opportunity to fill in the survey. We had 24 responses to try to help us understand, what does the community care about? Do you care about density? Do you care about thermal, performance, and at what level? Some of the other questions are about the number of SSDs. So I took all that data, and we're going to present the aggregate data here to kick us off. All right, so the first question was, what form factors do you care about moving forward? We have the current form factors, M.2 and U.2. We have the new ones, E1S, E1L, E3. And here's some of the data. We don't need to spend too much time diving into it, but it's interesting just to look at in an aggregate. So a few things really do stick out. So U.2 still has a lot of interest in it. M.2 interest may be waning. And then E1S, E1L, and E3 are the up-and-comers. We pretty much knew that. Power envelope. This one was also interesting. If you looked at power capabilities of M.2s, for example, that many of us adopt today, they don't have very high power capabilities. And if you see where the bulk of the requests are in this 10 to 15 and 20 to 25, it shows you we need to move away from the M.2 form factor to get to form factors that people care about. All right, width preferences. I may have put a few too many options in here. It was tough because, if you're looking in E1S, those are certain widths. If it's an E3, those are different widths. If you're U.2, those are different widths. Then M.2, I don't really know how you put widths in there, but you can kind of see it's all over the place. Nothing very exciting to get out of this, other than less than 5 millimeters and 25 millimeters, either really small and really large, certainly are not something that many people care about. Device depth in the chassis, so do you care about short or long? It seems like it's all over the place, no strong take there. And then this one actually surprised me a little bit. When we look at where you're placing it, in the front of the box, or the middle plus front and flexibility, and the flexibility option certainly came out more than half. So I expected a little more in the front only, but we saw a lot there. So looking at a few of the interfaces and some of the performance versus power, not a lot of key takeaways there, but this one stood out to me. So a by-4 is certainly very interesting. Nearly everyone said that's important to them, which is good. A few things, though, like dual port capable, we still have a lot of interest in dual port. There are a lot of industries that require that. So we need to make sure that we incorporate that in form factors that we're looking at. And a by-8 was nice to have. Very few people said that we need a by-8. So that's a lot of bandwidth when you go to Gen 4 and a really lot of bandwidth when you get to Gen 5. Ethernet didn't show up very much, and SAS SATA is also waning. And then here's another interesting one. You can see this nice little waterfall from the least amount of drives into the greater than 16 rate. So clearly a lot of interest in very dense storage systems in a node. It's also a little bit surprising to see, because sometimes you have high performance boot and caching drives, and sometimes you have high density systems where you're going after density. So certainly more towards the dense option. All right. So that was just a quick overview to get us started. So I'd like to share some opinions from Microsoft, things that we're looking at, some of our physical and thermal data. And I've spoken to a few of you that I believe also have some presentations and thermal data that you'll be able to share today. And I think it'll make sense as we get through our presentation that maybe there are some new options we really haven't considered. Bear with me. All right, so let's go right into it. All right, M.2s. I have no love for M.2s. I've spent some time with them. They're incredibly challenging. This is actually a picture from some of the M.2s that we've pulled out of an AVA carrier that we utilize in our infrastructure. Thermal interface material, incredibly thin PCB. It's flexible. I certainly have concerns on the components that are on there, the flex of the PCB. It's not easy to handle. I mean, there are a lot of problems with M.2. The good news is we are all looking at form factors that lend themselves to fixing a lot of these problems. So you're not going to have the handling issue. A lot of the casing options take away all the thermal interface material that you would have to touch when you're at a data center, which is problematic. So we're on the right path. So why do we actually care? So the things we need, the physical size, we want dense but capable enough. We want to make sure we can actually cool it. And this is not just at ambient. We need to make sure that the high end of our ranges, for example, in adiabatic data centers and a lot of hyperscale data centers, we're running in the upper 30s for inlet temperature. So it gets a little bit warmer in our boxes. I already talked about the M.2. We ran into a lot of challenges there. So we're definitely looking forward to the new ones. We have a couple different options on the table already. We have E1L and 2 widths. E1S, I'm only showing 2 widths for front serviceability. The other 2 are meant more for inside of a system. And then we have E3. Okay, we're starting to see a lot of form factors, but I see a lot of problems here. E1S, E1L, they're not the same height. We start off in the right direction. We started going for commonality, but that's broken. That doesn't make sense. If you're designing for an E1L or an S, you can simply move that system to be longer or shorter. You should be able to accommodate it. That's broken. We look at E3. Great idea to optimize for a 2U chassis. But if you want to have an E1S and an E3, you simply need more capacity. Again, you can't reuse your chassis design. You're starting from scratch. This is fragmentation. Let's see if we can actually try to bring these a little bit closer together. May not be possible. I know we all have different use cases, but it's something we should consider. You're actually going to laugh when you say E3/4 because you're going to see something in here that, hold that thought.
You also forgot to point out that E3 has a short and long version also that are.
Yes, they absolutely do. It's hard to show that without doing a top-down view as well. Then it started getting messy, so I left that one off the table. So what I want to start with is looking at 1U and 2U optimizations and maybe explaining a little bit how these different form factors are optimized. So E1 is great for 1U platforms. Certainly that's the optimization, and it will work in 2U. You can make it work, but it's maybe not as ideal as an E3 and a 2U platform. And again, E3 is the same thing. Optimized for a 2U, less than ideal in a 1U platform.
Questions? I guess the post
can't hear at the mic.
Maybe you couldn't hear.
Well, no. So we've had, because people are shuffling around, the mic's picking up everything, and it's recording all the clicking from people's laptops and whatnot. So what we're trying to do is unmute it, and when someone mutes it, we'll mute it and then unmute it as needed. It's picking up every little detail.
Okay, so maybe for questions, just raise your hand, and I guess we'll be able to unmute so you can ask your question.
That would be ideal.
And no mechanical keyboards. I think we'll do that then. All right, so a couple options here. I'm throwing a few things just to keep in mind. So showing a 2U system up there with E3, it's very obvious to understand where E3 came into play. Makes a lot of sense if you have a 2U chassis and you've got 2.5-inch drives in it. Seems like an easy fit. For 1U platforms, I was trying to show the comparison. If you may have taken an example platform, let's say you have 2 HBAs, maybe you have an OCP NIC for your network connectivity. What would you do for bulk storage and then maybe for a boot device? So on the right, E3 could easily fit here, coplanar with a board. You may have some E1S's, coplanar for boot and caching, and then the left side will be your bulk storage. We certainly like the E1 because you can have an orthogonal connector on the board, no midplanes, and you get really nice density. Seems to make sense. And if you look at the E3, if you start stacking them up, maybe you fit 8 over there in this example. That also works, but now you have a midplane. And then do you have that cabled out to something else? Do you have another backplane connector? So maybe on Gen 3, PCI Express, that would work. Moving forward to Gen 4 and Gen 5, that's going to be incredibly challenging without switches in the way. Do we have comments already? All right, Bill?
Yeah, but your E1 depends on the orthogonal connector, which is horrible for SI.
So so the comment is maybe that the orthogonal connector is not fantastic for signal integrity. I'll give you that. I have not looked at the data myself. However, if you're trading that with a backplane and cables and connectors, I would argue they're probably
We'll
fairly
say that there are more than one version of an orthogonal connector. I wouldn't say that they're all equal.
Yeah, but they all have about 3 dB of loss, insertion loss.
I'm not sure that we necessarily agree that they have 3 dB.
Okay.
But what is the insertion loss of a cable and backplane?
About a half a dB.
You have some really good connectors there.
Yes, we do.
Okay. So maybe if in your presentation, if you can highlight some of that, that would be helpful.
So that could then roll into cost.
Yeah.
Right.
Something that you didn't touch upon, but we've heard in the various areas, is that different host manufacturers who have different sorts of stand-ups and heights within the 1U are absolutely adamant that the E1 short works in their world, whereas others are making the E1 long work. And there are definitely different classes of customers out there today.
Absolutely. The E1 short gives you a lot of clearance. So this, I'm showing a 1 rack U equivalent. This is all to scale. So there's a lot of clearance for your latching design and interface with an E1S. The previous slide, you saw the E1L, and you're right. There's a lot less clearance. So for a structurally rigid chassis, sometimes, so there we go, it can be challenging. Absolutely. There are challenges in the design. All right, so let's talk about what we've been doing and what our opinion is. So E1L works really well for bulk storage. I mean, we're deploying that today, and we found it to be very conducive to our workloads. For E1S, when we want to displace M.2 local to a host, whether it's a boot type of environment or it's a high-performance caching, this is where we need to spend a little bit of time. 9.5 really isn't capable for our low airflow requirements. 25 is too large, and those are the two options you would think you'd consider from the spec. So we don't think either of these work, and we're going to go into why and share some of our data. So what we want to do is, what is the minimum width that could handle maybe a 20 to 25 watt workload? So you get the most density, and as you saw in the previous example, can you fit it under an HBA or maybe on top of an OCP NIC, so you maximize your front panel density. And then we still want to keep the idea of a double width version, and we'll show some of the terminology and what we mean by that. But for devices that may go outside of a 20 or 25 watt envelope, let's say it's a very high performance SSD or an accelerator that might fit in this form factor, we want to make sure that this form factor stays fairly agnostic, because again, E1S, it's a PCI device that's not SSD specific. I'm sure everyone in the room probably has other ideas on what they might do in a PCI Express form factor. And then we also need a scope storage class memory that'll be coming, now and in the future. So what have we done? So we looked, and we're going to start standardizing a few terms. You'll see us use this in our presentation, and hopefully these terms are consistent with what you've been discussing internally. If not, happy to converge on terminology. So SSD width, that's fairly self-explanatory. The gap is what we're assuming between the two devices, and then the pitch is centerline to centerline. And so what we've done is we decided, all right, we're going to sweep from 9.5 in the spec up to 15 millimeters for the device. We're going to keep the 2 millimeter gap, and then we show the effective pitch and then what the effective width of a double wide device is. So for example, if we made the narrow version, so instead of 9.5 to be 11.5 with a 2 millimeter gap, you would still have the ability to use a 25 millimeter device. So here's how we simulated. We took the 9.5, we took the 25, and we simply cut down the fins. We kept the asymmetric nature, and we ran our thermal simulations. And Brandon, in a few minutes, will walk through some of the data we've seen, kind of the sweet spots that we're looking at. And then if you have other data and opinions, something that may go point out some issues in the way we've simulated, or maybe in your environment that your airflow is substantially lower or higher, this is a perfect opportunity to start talking about that.
So asymmetric is really good for accelerators, and you can put your accelerator on the side with the fins. We poor SSD makers tend to use both sides of the board, and they're not thermally linked today. And so asymmetric is kind of half good.
So I didn't put that in this presentation. We were planning on looking at something where you have a semi-symmetric, where the secondary side may also have fins. So I don't know if you got that. So the secondary side, we didn't show it here, we thought about, should that also have some sort of fin? Maybe it's not as high as the primary. So on an SSD, maybe your controller's in the primary, your secondary is NAND, ECC, and other ASICs. So if you think you need a full symmetrical, certainly share that and the rationale looking forward the next couple of years. We'd love to see that. Maybe that's the next thing. There is a reason why we're thinking of having no fins on one side if possible. So if we want to do it coplanar and put it under an HBA like you saw on the previous image, it might be a little bit easier to do if you have a flat surface. And fins don't preclude that, though. So if you wanted something on top of a PCB instead of straddle mount, smooth might be better than finned. Ross?
I would also argue the controller is the hottest part on the device. And so that controller is on one side. As long as you have a single controller in NAND, that asymmetrical is a good option.
And, for all the SSD and NAND creators in here, can you actually cool it for the next 5 years on the secondary side with an asymmetrical? This is the feedback we're looking for. You know your devices, you know your formats. Help us understand that. Let's make sure this is not a dead-end form factor.
Given that I've peeked at what else is coming, one of the interesting things you bring up is what the difference is. And if the difference is what's tolerable for heat matters more for the NAND or for the controller. And in the example, it turned out to be the NAND.
Our data is
That's actually part of the discussion point.
Okay.
On your table, what drove to the assumption of a 2 millimeter gap?
It's some of our chassis design and thoughts. So, Brandon, do you want
to talk about it? I'll talk about it when I.
Okay.
Do you think it's too big, too tight?
No, I mean it's on the order. I think right now at a 12.5 millimeter pitch for about 3 millimeters
with a current 9.5. So I mean, if we think this is too tight, we can certainly talk about it. I mean, it's really into the chassis definition and then what is the double width definition. So if we can converge on what that should be, I think we're flexible. I mean, we're not set on 2 millimeter. Our devices, our designs that we're using right now, if 3 makes more sense and everyone aligns to 3, fairly confident we could handle that. All right, so I mentioned about not creating a dead-end form factor. So I talked about it. E1's a container for PCI Express of something. Right now we're talking about SSDs. Can we also think about what that might be used for? Kind of the obvious answer is accelerators. What would be interesting is instead of creating yet another form factor for accelerators, if you can fit in an E1 or an E3, you're good. But there may be challenges, and I've spoken to a few people that think there may be something else we should consider. And I would argue if we do that, maybe we create this E1A. Basically, it's an E1, only grow in the height. So maybe not fully to an E3, but maybe it allows you to do something like putting it over an OCP NIC or an HBA. May not be the best idea, but if others out there have applications for accelerators, can we at least keep it very similar to E1? Because if you imagine you built an enclosure of 1U for SSDs, and you want to leverage some of that work into an application for accelerators, it makes sense if you keep the same connectors. We already are scoping a by 8 in E1. It's already there in the spec. So, I mean, it seems conducive to avoid yet another form factor, although technically it is. At least it's related versus completely orthogonal. So ideally, that would be a nice outcome. All right, with that, I'm going to turn it over to Brandon. Good to go? All right.
Okay. All right, I'll introduce myself because I haven't met a lot of you. Oh, hey, Paul. Met you a ton of times. So I'm Brandon. I'm a thermal engineer in Azure Cloud at Microsoft. One of 2, so if I'm tired, it's just because I've been doing emails and this, if I stumble on my words. But, So I've spoken to actually multiple companies about how we align our thermal simulations. As you know, there's multiple tools out there. I mostly use FlowTherm XT, but a lot of people use FlowTherm and IcePack, and so they assign free error ratios, and that's going to impact thermal inlet airflow velocities. So what I tried to do was come up with a standard way of analyzing the drives with it being agnostic of system design and thermal practices. And so there's been kind of a lot of flack, but we've kind of converged. So as you know, everything in thermal is about constraints, and we try to give people headaches and go with the most unreal number that we can find. That happens 0.0001% of the time. So that's what we did. So for spatial boundary constraints, we said 25 millimeter. That's been the talk of the town. That's the widest ruler or SSD drive that we've seen. 9.5 is what we've used internally, and we've done some analysis there. So there is everything in between those drives. Where do we need to be, as Jason questioned earlier? So 25 millimeters, that sets the boundary constraints. Basically, mechanically, we've seen 2 millimeter pitches, and it's because of the way that we set our dividers. It's basically just a wrapped sheet metal that's extruded in a ruler cage. So we figure that's the go-to. I think some of our platforms we use 2.5. 3 is significant, but you don't necessarily see any benefit from a flat plate with extra 3 or an extra millimeter of space, and I'll get to that later. So then for airflow constraints, what I did is I scaled the airflow to get the coolest drive to 20 watts. And the reason being is because 20 watts was the target, and I could set a really high airflow constraint, but everybody was worried about minimal airflow requirements. So I figured as a system designer, if you wanted to expand this domain in a real system, you could do that. But I just needed to come up with a consistent airflow target. And so I targeted the 20 watt workload for the cooler drives. The other thing about this is for these outer drives, because of the way Therm XT works, it's not a mirrored condition. So you're just basically heating this space up, and it doesn't act as the cooler drives towards the rear or towards the center because you have a really high ambient on the outside. So that's pretty much the setup. Does anybody have any questions?
Could you explain that last bit about the end being higher?
Oh, yeah. So because of the way Therm XT works, is this is a closed boundary. So it's pretty much adiabatic, right? So you get these drives on the ends are the warmest, which, I mean, you would see in a normal system as well because you're being closed into a ruler cage. And if you look at the local ambient sweeping from the outer to the inner, it's getting cooler and cooler and cooler. So this drive ends up being the highest power. So I was able to get 24 watts or so out of this drive, and then these would be at 20 watts. But I just wanted to scale the airflow down to the minimum amount for the coolest SSD. And then I was just going to that's the airflow that I use consistently for all of the drives. Because if I so some of the simulations I've seen, they just say 105 LFM. And the question there is it 105 LFM into the domain? Is that through the channel? And because of traditional analysis, it's only been one SSD. So you would have similar airflow in and out. But when you start to consider that in a system, the fluid boundary layer is going to be constrained by the device next to it, then that airflow starts to change because your impedance is going to change as you vary the width of the drive.
So on the N1, do you have a half gap or a full gap?
So on the N1, there is a full gap here, right? And so you're going to be constrained to like a tube flow anyway, whether it's this side or this side. But because you are getting turbulence in the center and you're getting more laminar flow on the outside, these are proving to be cooler drives on the inside, just because you're not getting turbulent mixture.
That seems backwards, though, because wouldn't all these drives cross-feed each other to get to the end? That last drive on the end doesn't have any cross heating from a drive next to it. It's cold, right?
So that is true, but on the bottom side where we're actually seeing that's where the warmer NAND is, right? So you're actually just getting preheat through the board. And so, yeah, you're seeing preheat between these drives, but because of this side not being able to remove any heat because it's laminar, then you're actually getting a lower convective coefficient.
I'm not sure I would agree that's laminar. You've got fans in this system that are blowing very hot.
But I don't have fans in the domain. This is just me setting a domain velocity. So it has to be agnostic of a system. So I could have set the airflow velocity based on a dual rotor or a single rotor fan, but then it would be Microsoft system. And so that wouldn't be your system. And the reason why we even changed the way that the M.2s were analyzed in a domain is I talked to Paul about this before, and we were talking about just what does it look like when you analyze a single SSD versus putting 3.
I agree. You need to have at least 3 due to the cross heating, right?
Correct.
You need to. The way we would normally do this is, and I'm not sure how Flowtherm XT does it, but we would normally do half gap on either side and have that be a boundary condition that you have half the flow going across.
So half gap won't remain consistent though. So if I go to my mechanical engineer and I say, can I have an extra 2 millimeters because in a 25 millimeter domain, I want to add an 1/8 SSD at 9.5. Like this is just spatially constrained. And they say, no, you can't have it. Well, then you're just going to lose this half width anyway. So this is just to set the inlet airflow. There's going to be some simulations where this gap doesn't exist. And because mechanically, I don't necessarily always get that gap. They would just say, you ride that SSD along that wall, it still support it. You still get your total width. And so that's why I wanted to set the spatial boundary. So the one good example was 15 millimeters. I could have gotten 6 drives, and if I just expanded the boundary by 0.5 millimeters. But it's still outside of the domain of where I'm mechanically constraining my components. And I didn't want to have multiple variables. I wanted to keep constants for both airflow and space.
I think by constraining your spatial boundary, you are making it more complex, right? You want your drive vendors to be able to spec a drive based on what its capability is, not how you're constraining the system. People have all types of different systems, right?
Sure, you could set that, but you can set that constraint based on the inner SSD. Now, however you design your system, I can't use Microsoft systems and say, Western Digital, Intel, this is what you set your spec to. But I can say set the spec based on the spatial bounds and whatever is the best performance that you get out of the SSD at constant airflow, considering cross heating.
Now, aren't you changing your impedance and making that a variable?
Of course, the impedance is changing, but then if I give you an LFM for a single drive and I say that this is the airflow required for a single drive, technically that drive is going to look better than if you consider cross flow. And I have to consider cross heating in that space with variable widths. And then you as a system designer can say at 14 millimeters, I get over 20 watts average for this drive, as opposed to a 13% optimistic number where you're not getting what you need based on LFM that doesn't consider cross heating. And that's what we saw. There was a 13% improvement when I ran a single drive by itself with a 2 millimeter gap between the surface of the fin and the surface of the opposing plate. And so if I give you that drive and I say this is how much airflow you need and you put it in your system and now you're driving your fans by 13%, you've got a cubic increase of fan power. Whereas this is much more resemblant of what we would see in the system. So we've run the 325 millimeters and put it in some of the systems that we currently have. And we saw that we needed the same through card airflow. And the one thing that I'm not defining actually is inlet airflow. It's through card airflow because of the different simulation tools. For instance, I want to speak to the different tools. So for flow therm, you may set a 50% FAR, right? But then you just have these two big bulk openings. Whereas if I use flow therm XT, my FAR is still maybe 50%, but it's not being forced into one channel, right? I'm not getting really high CFM or really low CFM through one channel that has a block off plate or something. And so that's up to the system designer to how they want to analyze it. But what we should know is what is the impact for through card airflow at varying widths, and what is the average across those different widths, which we've seen the average LFM required to cool from 9.5 to 25 is around 73 LFM. I believe 70 to 109 was the target.
One more slightly question along these lines, but it's slightly different than what we've talked about so far. So one of the things I just heard you tell us is that you've looked at a larger system than 3. And I wondered if you could give us a rough idea of how much cross-heating matters. In signal integrity, we've learned we have to worry about near neighbor crosstalk and far neighbor crosstalk. Do we need to go to 5, or is 3 good enough? Do you have results to show that 3 is good enough?
So we'll go to the inflection point of width versus power. For me to tell you in my...
No, I meant looking at 3 devices in the domain versus 5 devices in the domain.
Yes. So
okay.
What is the output you want to know? The power that you can consume for 3 versus 5 in that domain?
No.
Okay.
I care about the temperature of the guy who's at the worst, which I presumed is the guy in the middle. So okay. If I have to account for how many out in the cross heating.
Right. So the way that we scale is I've taken the worst temperature and I've scaled to the worst component, and then that will give you either the maximum power that you can get or the minimum power that you'll get in that domain. So let's say in that domain for 3 versus 5, if 3, your minimum power that you will achieve is 30 watts when you scale to the composite of the least margin composite, then you get 30 watts. But let's say the maximum power you can get out of one ruler in that domain is 34 watts. Then that gives you the margin, your operating margin, and then it's up to you as a system designer to expand the pitch if you need it.
So let me answer, I think I can help you answer that. So if you look on the left, you're simulating 325s, but the one on the right, he was simulating 7 of the 9.5s. So anything smaller than 25, you start getting more. So some of the data he's been looking at has, for example, 6 to 7 devices, and we do see some variance. I don't think we're going to show that in the presentation right here, but we have.
From a device maker's point of view, I expect that you're going to run all my devices at my rated power, not that you're going to run one at 20 and one at 16.5. I don't know if we have that kind of capability to offer you. So I'm not sure that presuming different powers for different slots makes sense, unless that's what all the system makers are asking.
Well, no, but the simulation uses a constant power for each drive, but you're going to have different pressure drops through each channel depending on the layout of your system. So, for instance, let's say, I don't know, I have a system where my power supply is on the right, and I put my ruler on the right. Then I'm going to have a lot more pressure or a lot less pressure drop, a lot higher pressure drop where my power supply is and my right ruler is. So that ruler on the right is going to be higher, and the ruler on the left is going to be cooler, right? Switch it to the opposite side, then the ruler on the right is going to be cooler, the ruler on the left is going to be higher. But again, if I come to an open compute conference and I say, based on my system and the way that I design my system, this is how your ruler is going to interact. It's not fair to you. But if I just give you an open domain where it's agnostic of any downstream temperatures or airflow impedance, then you can start to see where the worst ruler is, or the highest ruler temperature is, lower power temperature is in that domain. So I'm keeping gap consistent, right? I'm keeping domain consistent. I'm keeping airflow consistent. And so I need all of these to be consistent to get an input and output. Input being the airflow that you're getting through the device, output being temperature. So this is the hard part to agree on, because you can change all of these different parameters. Like I could go to 15 rulers, and if I have 0.5 millimeters open gap, I could just expand the domain, right? Or I could say, no, I don't get 15 millimeters, I get 6.
I have a question. This is David with Western Digital. By measuring or at least fixing the airflow, the local airflow across the drive instead of the inlet, does that constrain, are you assuming that we constrain the design of the drive thermally so that we keep the pressure head the same from drive to drive?
I don't at the moment, but my apologies. I think in general, one of the things that many of us are looking for is we have way too many thermal methodologies, and we do need to agree on one so that we can effectively have at least the touchstone how we get there is still what we're working on.
Yeah. Yeah. And to your point, we had a graph. Oh, go ahead. You had a.
Well, just one observation too. I would say, you really want to be in binary numbers, right? So 7s and 3s don't make a lot of sense when you're getting 5/16 off the top, 5/3 down to 8s, 4s.
This conference will now be.
And sure, that's true. And you could expand the domain, and there's a spreadsheet that this doesn't go into that looks at if I added one more 25, then I would be at 110 millimeters, as opposed to if I do bifurcate and go from 7 to 8, I'm still kind of within a reasonable domain that maybe a mechanical engineer can move a PCIe riser somewhere out of the way. So if I'm at 83 millimeters with 9.5, and I want to go to one more 9.5, I'm only at 93.5. Right. So it does. I mean, you can play around with the Wisps, and that's something that we should consider when setting the domain boundary. So yeah, it's just another data point to look at, and I don't disagree. Right. And so
if I end up at 17, that doesn't make any sense.
Well, so that's kind of one of the other goals we were trying to satisfy was to come up with a ratio of Jason said double height or double width and single width, or double wide, single wide, but also to come up with a ratio to say at 3 rulers, what does that look like? 3 25 millimeter rulers, what does that look like for 11.5, right? And so when you start considering how many rulers you need in your system and then what your TDB targets are, then you can say, okay, if I need 625, this is what it equates to for 11.5. Do I meet the power requirements that I need?
I have a question.
And so let me go to the next slide, because I think this will kind of
this is David.
Show
I have
what
a
we've been talking
regarding...
about. Oh, it's not changing.
I have a question. This is David. Can anyone hear me?
It's a hot topic.
David, I can hear you, but I don't know if you're hearing us in the room.
Okay. My question is regarding...
Scott, did you touch that?
I did not. I don't break electronics, just not electronics.
Actually, yeah, we'll go through here and then we'll get into the data. So, to your point about the finding the warmest NAND, it is on the opposite side of the board where there are no fins. It is consistently NAND 4. But basically what we did is the SoC actually had the highest margin, as you said earlier, and DDR had the second highest margin, and then NAND had the least amount of margin. So we just scaled the power of each component, saying that if the NAND can only accept this many instructions, then the SoC can only process, or the throughput from the SoC can only be this much. So we scaled the power, or I scaled the power of the SoC, the DDR, based on the NAND because it had the least amount of margin. And then that gave me the overall ruler power. The one thing that it was agnostic of is the change in the inductors and, on the board. So we kept that constant as I think it's like 1 watt or so. So inlet temperature was 35 C. Inlet airflow velocity was held constant, and then domain area were held constant based on the previous slide. So I think this is what you were interested in when you called out, 3 versus 7 drives in that domain. So you can see that at 9.5, so basically this orange line is the total power of all of the SSDs in the domain, in the constrained domain. The blue line is going to be the highest power for the ruler in that domain.
Hey, Brandon, there's a question online. David, can you hear us? David? Okay, his question is with regards to the local airspeed or the through airspeed over the device as opposed to the inlet airflow. His question is, how does a system level designer plan to keep track and measure that so that these assumptions maintain integrity?
So we characterize our systems with anemometers. You can measure the inlet airflow and the outlet airflow through that channel. We tend to look at the pressure drop across the entire system, and then we can calculate an operating static point, at least within inside of the system. Now, in terms of integrity of this simulation, we the initial simulation to make sure that the tool was accurate is we took four different regions across 12 rulers, and then I took the through card airflow of 3 of those rulers in the worst channel. And so then I took those 3 rulers outside of the system and placed them in a domain and matched the inlet air velocity to the outlet air velocity to see if the domain simulation was similar to the system simulation. Internally, we've done system correlation, and we've taken the standard deviation across all of our components. That's M.2s, that's PGAs, rulers, CPUs, and we've correlated the simulation to our empirical data, and we've seen a correlation of 97% or so to our real-world test.
Thanks.
Can we do a quick sound check? Can
Am I heard
anybody
in the
on
room?
the WebEx talk to us?
Am I heard
we
on
can
the
hear
in the
you
room?
guys.
Can you hear us?
Well,
Well, they should be technically. They can
Jason?
hear each other, but they can't hear us. Or we can't hear them.
can anybody on the WebEx, can anybody on the WebEx
I'm
speak and try talking, see if we hear you?
speaking.
So,
David Wright is
David,
speaking
this
right
is
now.
Mark.
Just David, right?
Yeah, everybody on the
Nobody
phone
on the
can
WebEx
hear,
can
nobody
hear.
in the room can.
We can't hear them, so.
Or it's a go-to, yeah. Yeah, we'll try and fix it.
Okay, can someone on the WebEx say something?
Hi,
Yes,
this
I'm
is
trying to
Mark.
say
Can you hear
something
me?
right now.
All right. Okay, so I think now you can,
Now we can have an interaction.
yeah, now
Okay.
you can interact. We've got about almost 60 people on the WebEx, so quite a lot of people.
Okay, so this is David, and I believe you were responding to my question regarding the local temperature or the local airflow and airspeeds over the device. So if I heard correctly, you're trying to measure the inlet and the outlet, and then you're trying to use the pressure head in order to adjust for what the local airspeed is going to be over the device.
Yeah, so the local airspeed over the device, are you questioning the system or the domain simulation?
The system.
Okay. Yeah, so the system simulation, if we go through the process, we don't know the local airspeed of every single drive. What we can do is we can place anemometers in certain regions or certain channels behind the ruler chassis that we have internally, and then that anemometer takes both airspeed and temperature. So we can correlate from the simulation to the empirical test the airspeed and the temperature through that section of our system if we to get more accurate data. So that's more of our localized method and how we correlate empirical to simulation.
So I'm trying to project here, if it's being proposed to the industry, what kind of local speeds a device designer should consider in order to mitigate or to manage thermally their device. How would we keep that going forward if the designs are going to change from one to another? How are we going to be able to measure that? Does that make sense? What goes in has to come out, but then over the drive itself, it's going to be different speeds depending on what kind of design a device designer is going to choose, right?
Understood. So that's why we would have to come to a conclusion on what we think is the highest constraint of speed required to cool the drive. And you should have the measurement equipment to at least meet that constraint. And then, so that's where the spec is being set, is at 24 watts, if you need, 115 LFM for 15 millimeter drive, then that's your requirement. But it's set within the spatial. Go ahead.
You're considering that to be the local airspeed over the drive, 115. Correct. Or are you considering that to be the inlet?
No, so the reason why I can't use inlet is because inlet is going to change with your pressure curve, right? And so that's why I'm using through channel velocity as opposed to your inlet velocity. And so even internally, we so if we engage a supplier, we do give inlet, of a certain airflow velocity. But for our system, that would be different for our system versus yours. But the one thing that shouldn't be different is how much heat or how much air or fluid it takes to remove that energy across that drive. Right. And so I can't assume that if you have a paddleboard connector to a 20 millimeter ruler, then that's something that, the system designer is to optimize. But to be agnostic of the system, I can only characterize the drive itself, not including any downstream impedances or the free air ratio of your grill for your inlet. And I think a lot of the questions that I get from thermal designers is from a perspective of their system, and it's hard for us to universally set a spec from a component perspective when I consider my own system.
So the goal is to share. The goal is to share what local airspeed all device designers need to meet from a worst case perspective, and then system level designers will make sure to maintain that.
Correct. And so the control, what it sounds like, are you asking what is the control point here for the SSD drives for you to measure to? Okay. Correct. Yeah. So the control point is why I chose the spatial boundary, because we know that the pressure is going to change with the width of the device. So if I have 8, 9.5, that's going to have a really high impedance as opposed to 325s. And so your pressure curve is going to be totally reliant on how many rulers you have in that device, agnostic of what components you have downstream. And that's what you should measure to. So if, Intel or Western Digital say that you need 150 or let's say 70 LFM through a device, and you put it in your system and you're finding that you're only getting 60 LFM through that device because you have a bunch of cabling or something behind your ruler cage, well, then that's up to the system designer to optimize to meet the power requirements of the module, not the device supplier.
Yes, agreed.
Okay.
As I look at this chart, forgive me, I'm struggling. As a mostly protocol guy, I'm trying to make sure I understand it. I'm not seeing something which tells me what the difference between SSDs in a given chassis are when you have the cross rating. I'm seeing the total rating for as balanced out over all the SSDs in that chassis. So I'm not seeing the differential, which is actually where my question was coming from. I was asking if we device makers need to look at 2 or 5 or 3 or 5 devices to understand crossing effect.
Right. You want to see what is the highest constrained device in that section. Right. And so you can do that with this. So let's say you took the simulation. I just gave you a file and you open it in Therm XT. You could go look at every single drive and you could say, okay, for 9.5, 20.3 watts is not the constraint. The constraint is actually 16 watts. This is what you will get in this domain with this pitch. Pitch is going to change, but the gap should stay the same if you're using 25 millimeters of the domain. You can do that. And so I have the data showing.
You're telling me the system results. What I'm trying to figure out is for device building, when we do our cross simulation, what do we have to do?
But this is only your component. It's agnostic of a system. I don't have any downstream components.
So I think I know where you're getting at. So what our intent was not to model a system. Our intent was to figure out what the right device width is. So we actually do have the data that you're asking for. Ours is for a particular vendor, a particular SSD. This is why we're not showing it today. So what we're proposing is we have a spreadsheet that walks you through the inputs, the outputs, and the simulation. We're going to clean that up, make sure there's no data in it. Because for each vendor, your T-case, your TJ are all going to be different. And we're hoping that you'll come back with data to show that something works for you as well. We're showing our data in our platform with one vendor at the moment. We can expand that out, and we encourage you to do the same thing. We can't share vendor data, obviously, so that's why it's not showing.
I just have a simple physics question. How is it that you can increase the weight of the device, yet the power goes down, the maximum power goes down?
Which one? Are you talking about the domain power? Because the domain, the device power did not. Oh, yeah. So this, no, it was because, so for 11 and a half, for 12 and a half, I had less air gap between the ruler chassis or 25 millimeter domain than I did for the 11 and a half, but it's also only 0.2, so it's probably within the simulation tool before it finishes. There's still some oscillation when it's doing its flow calculations. So, I mean, it's not, if this was 2C difference or a 2 watt difference, I would agree, but it's 0.2. 11 and a half versus 12. 6, yes.
Think of this as exact numbers. We're looking for sensitivity, like at what point is it wide enough to accommodate the power we're looking for? And then once you start simulating, you look at your own data, different vendors, different system designers. Let's make sure. Yeah.
This is E1.S.
So every time Brandon says ruler, just translate it to SSD, E1S.
You can also slap me. That's the agreement. But
All of this is at 35 degrees C?
Yes.
But wouldn't it make sense for a drive vendor who wants to sell to multiple markets to have a curve of PLA versus velocity and to be able to find out, look at their pressure drop versus their velocity with their system curve and determine where they lie in that? Because you're going to have people in the HPC market that are going to be running way below 35 degrees C. You have enterprise guys, compile guys. So I think providing curves instead of a point would make it easier for people to be able to look at drive vendors' capabilities. So this is the drive I want, or this is what performance I get at this.
So I think I don't for a couple other presents. So some of the vendors actually have some of that data. So I believe Western Digital will have a curve. Ross, I don't know if you want to show yours as well.
Well, hold on one second though. Yeah. I just want to get to that. So again, this is a different approach, and you can get that same data to say that with this mini SSD, with this width SSD in that 25 millimeter domain, this is going to be your pressure when you only look at the drives at a standard gap, which we haven't agreed on. I just used 2 millimeters. So it's the same, you would get the same specifications as a single drive. But again, with a single drive, you don't necessarily understand what the pressure change is over time.
If you use the 3 drives, then you look at the middle drive, and you come up with curves of that stuff. It's not looking at a single drive. I completely agree that's not what we want to do.
So the pressure curve that's in the spreadsheet, it looks at the domain pressure at the rear of the drive with the change in widths, right? Because that pressure is going to change as the heat sink height changes. So you could provide it for each drive, but give the highest pressure drop for the middle drive, if you like, or you find the worst drive in that domain. So yeah, I mean, basically the point of this study wasn't necessarily, like I said, I could pass this to you and you could take the model and you could figure out your pressure curves for the worst drive. But the point of this was to see what is the point of inflection as I increase my width in a certain domain. And we do see that as a system designer, if, you know, your EGs say, I need this much compute power and I need this much total bandwidth across drives, you can say that, okay, going from 12 to 14, I'm going to have to knock a drive out of this space that my mechanical engineer has given me. But then if you go to 15, which is the same number of drives, then you get both increased drive density and total domain processing power, or IOPS power.
Do you see any threshold of, we must have at least have this number of drives for sure?
No, that's up to your EGs to determine. I mean, your software engineers or your AI scalers, those are the people who are going to determine your power requirements for the drive, right? And so maybe you don't want to pay for 25 millimeter heatsink and you do need 24 watts. That's your requirement. Well, then you have a table to look at and say at 24 watts, this is what I can choose. Okay. I think Paul.
Brandon, just a quick question on this one. Was this, these results, are they based on a fixed CFM, fixed velocity, or a natural operating point based on impedance of the heat sink as a function of the spacing, which would occur there, and the fan operating curves and the natural delta T that they would see?
So I didn't choose a fan curve because, again, that's up to the system operator. The limitation was the previous slide was to at 20 watts, what was the minimum amount of airflow that we needed with the highest impeding ruler width, which was 9.5. So go ahead.
So it's fixed CFM or fixed velocity?
Fixed velocity.
Okay, and that's channel velocity or approach velocity within the...
That's approach velocity. Channel velocity is going to change with the width of the ruler.
Okay, so velocity between channels is roughly the same as fixed. Well, not fixed, it's somewhat fixed. And your free area range is changeable, but it's a variable.
Correct. Which are the, I'm sorry, the gentleman with the, I'm sorry, what's your name?
Glenn.
Oh, Glenn. Yeah, which is the point that Glenn was making, is that you can form a graph for each ruler width, take the ruler with the highest pressure drop, and then choose your ruler architecture based on that.
A question from my people. Was there a tunnel length that you used?
The tunnel length was, I'd have to look at the simulation. I think it was like 183. I left enough space so that at the end of the tunnel, you were returning to the ambient condition, the ambient air temperature, and you weren't just heating the devices within a small cabinet.
If we do look for a common methodology, that's probably something we need.
Sure. Yeah. So I guess your engineers are probably referencing, like, if you do natural convection, you want like a 2-to-1 rule where you expand out.
You know, we're just looking to define how hard act in a given environment.
Okay. Yeah. Yeah.
We're hard people, not system people.
Yeah. Yeah. That will impact, yes, that will impact the pressure that you get. If I had a domain that was really close, then that would change the temperature. Okay. I think that's, let's see, this is broken again. Oh, it's paused. Where's the, click.
So, this is Ivanovich from Lenovo. Is the upshot of this is that part of the, whatever new standard comes out, there's going to be a methodology that's going to be part of the standard that says system guys, drive guys, this is how you calculate all this stuff? Is that the idea here? Here's the process.
Sorry, could you repeat your question? I didn't. Yeah.
So the upshot of all this is part of this proposed standard or whatever, there's going to be a methodology section for configuring, measuring, whatever, this kind of information. So system guys, drive guys can make decisions. Is that the idea? We're going to document all this?
That's correct.
Not the specific study, but here's the steps you got to go through to get to an answer.
That's correct.
I would say that that's part of the goals of some of the folks here, that we do want to get to a common methodology, because certainly it's obvious that our methodologies for measurement vary, and we want to be interoperable in what we do. So once we decide what the right widths are, we should have a common way of figuring out how well we do in our common method. Trying to answer that question.
I think the other takeaway is that maybe once we've figured out the methodology, if someone builds an enclosure to correlate the data, we can then make sure that anything we simulate in ideas are actually correlated. So if we have volunteers, I know correlation's a tough one.
Yeah, and I think, I guess part of the reason why I wanted to set a drive count at the widest space that we could get was kind of, to your point, was the optimism of the TDP of a drive when you analyze it by itself. Mm-hmm. Whereas if we can come to a common agreement of how we choose the lowest TDP drive and set that as the specification across the board, agnostic of composite temperature limits or whatever, then we can push that spec out to system designers, and either it improves or the system just doesn't meet the specification. So, I mean, that's, all of these other things, these other simulations, we just kind of ran internally. Manish had a question about, Manish had a question about the ruler pitch and what that impact would be on a flat plate. Obviously, it's not going to change much. If you add fins, it's going to get drastically better. But we could at least see, if we change the pitch, how that would affect a vendor's simulations and specification changes, right? I think the other takeaway from this is we all need to come to a common agreement on what that pitch is, based on what mechanical engineers typically design to. All right. And then lastly, again, mainly it's not about the data. I guess it sort of is, but it's the methodology of where do we set as upper and lower tolerances for airflow and pressures. I think that's part of the spec that needs to be added or at least analyzed. So
when you just ran when you say pressures,
or impedance curves, sorry, yeah, impedance curves for the drives.
That's a hard thing to define, but essentially when we design thermal solutions to operate at across the plane of the impedance curve and the scaling band curve, and if we, basically that'll be the CSM that we actually get for a given platform design. So maybe the way to think about it eventually, and I'm sure we can get there today, is that we're designing a thermal solution relative to a thermal performance we're trying to hit that has an impedance curve for that. Because that'll be the natural operating point relative to a band curve.
Right, and you need to so we also need to agree on which drive do you develop that impedance curve on, right? Because I could use my domain impedance curve, but that's not relevant to the worst drive that needs to be cooled. It just basically tells you what the impedance curves of all the drives are. Again, it still is going to be more pessimistic with this kind of analysis as opposed to a single drive. And so what I'm trying to prevent, at least internally in Microsoft, is we get impedance curves and we go calculate our flow rates from whatever fan vendors we get, and then we go deploy it into EV and test it. We're like, okay, this isn't right. We're 7% or 8% higher than what the supplier is telling us. And so hopefully this saves us an email chain because we're just like, oh, this is better than we thought it would be. But that, again, that's something that we should come to an agreement on.
So maybe it's part of the methodology for empirical testing and also developing methodology for modeling so that they go really well and actually measure empirical
Yeah, I think it's both. And again, up front, if we agree that 3 drives are going to give you your center constraint for the widest drive, once we characterize that and we can match an empirical result to a simulated result that we have a methodology for simulation, then I think going forward, we can be confident in the specifications that we develop over time if they continue to have high correlation. But if you're volunteering to make this chassis, that would be great. We thought to have it internally.
Let me just quickly let me up-level this just a little bit so that we're not monopolizing all the time. So quickly before we hand it over to the next presenter, thanks, Brandon.
Oh, yeah.
Essentially what we're seeing is that somewhere in between this 11.5 and the 15 seems to be a good sweet spot for this generation, hopefully another generation to come. Looking for everybody else, look into your roadmaps. If we're utilizing these devices fairly heavily on the right path, where are we going to be? Are we missing the boat? Are we going to be in 2 years saying, wow, if we design for, let's say, 11.5 and then we end up at 28 or 30 or 2-3 years from now, have we built a form factor that is either require a lot more airflow or going to that double width? So we need to make sure that we're forward-looking, make sure this actually sticks with us.
In your first slide, you said something about moderate.
Depends on the generation. And so the reason I said moderate is to leave that out a little bit. So for larger capacities, you're probably looking at an E1L or an E3, something that has much more real estate, or NGD somehow managed to pick in 16 NAND packages. That's impressive. So there are opportunities to put higher density, and then with stacking, that's going to continue to go up every generation. So with that, I just want to say that we've already seen a lot of these devices. So I have 3 at least here today. So Samsung has a 25 millimeter E1S. We have Intel's. We have Western Digital. All slightly different in the way the heat sinks are implemented. That's going to change your pressure drop. But they're out there. We just want to make sure that we're catching this sooner rather than later. I'm assuming that everyone building a device doesn't want to invest in a thermal solution and then after the outcome of this, go back and redesign it, and then we tweak it again and you grow it or shrink it. The goal is let's converge as quickly as possible. All right, with that, Billy, good to go? All right, so now that you've seen a hyperscaler, at least in our opinion, kind of things that we care about, let's bring it to some of the large storage server vendors that may have a slightly different opinion and different priorities.
All right, how do I share on this?
I'll make you a presenter.
Hey, Jason, do you need me to do it?
That should be able to do it.
Okay.
There we go. All right, you should be a presenter, so if you want to, instead of sharing screen, you share the application. And while Bill's doing that, I think we have a few others that will have some slides to share later. So I believe WD will. Okay. All right. We have a slide, perfect. We have NGD. Anybody else have slides to share? No one in the Intel camp. Very quiet. All right, we can wait. Yeah.
Now this is an entertaining thing. I fill in. I'm a distinguished engineer in the Dell server group. I'm part of the server advanced engineering group at Dell. But notice the title of my presentation. Mr. Kaler.
How coming up? I didn't realize you were just going to show my slide.
Hey.
He's using carbs.
All right. So, hey, guys. So, folks that don't know me, I'm Paul Kaler with HPE, an advanced storage technologist there. Who's going to control it? Jeff? Jeff? All right. Okay, so basically we were kind of asked to come and present why we're interested in E3 for a form factor for us. So it's fairly simple actually, and it's I'll kind of go through a little bit of detail, but really primarily it's because 2U servers are our volume server, right? So it's really around getting something that's optimized for 2U. So you can see here kind of the E3 form factor was designed to be very specifically modular for easy transitions from the 2.5-inch and 3.5-inch world we live in today. So here on the right-hand side, you can kind of see an example, one of our 2U servers. It's basically got our 2.5-inch SFF U.3 drive cages, and then it's got different drive cages for E3 short, thick, and thin. Those can be interchanged. So, I mean, really, it just comes down to the fact that for us, our vast volumes are around our 2U servers and not our 1U servers. So clearly using like E1 short would be very inefficient for us because we'd have tons and tons of devices, lots of PCIe lanes to route. It'd be very difficult. And then thermally, there's some advantages, right? We gain when we're in a 2U box, you can scale your capacity just like if you had stacked two E1Ss on top of each other, but you don't have a backplane for that second one. So your capacity, your airflow and thermals is really, really good. So it enables you to scale your capacity without having to scale up backplane connectors and other things that add cost. So for us, that makes a lot of sense. Really on the mix and match is one of the big benefits that we see in E3 is as we move forward with new interfaces like CXL and Gen Z, both of those, we can take advantage of these really high performance, up to 70 watt type devices. We are enabling also the ability, we've kind of shown a snapshot here of how we're going to do this, where we can leverage all the same mechanicals so that we can swap a E3 thick in the place of two E3 thins. So that allows us to take, all leveraged mechanicals, use the same front end, swap out a back plane, and now you've got the ability to easily go back and forth between different configurations for customers. And clearly that enables us to go beyond just standard NVMe drives. So as we see more and more devices coming out that are Gen Z or CXL, whether they're DRAM devices, whether they're accelerators or higher power devices, those are the other reasons why we see all that, highly leverageable with the same form factor. Clearly that reduces cost. The more leverage we can do, that enables us to reduce cost to the customer. And also we can saturate, we kind of look at how much bandwidth we can pump through a 2U server, even a 1U 2P socket server. A lot of it is how much bandwidth you can pump through there. And the more devices you get, the more performance you wind up leaving on the table if you can't really take advantage of it. So that's one of the things that we've seen is in a 1U server, you kind of get, we're about 20 drives. We're already getting to the point where that's well beyond what a 2U server can pump through it, approaching 1 million IOPS per drive. So those are really kind of all the main reasons why we are looking at E3, thick and thin, primarily. And I think for us, we see the short as having enough capacity between the thin and the thick, so we don't really need to go to the E3 long. I think Bill will probably say they have a different opinion on that. So I think, but this is something that, at least for us, we were trying to kind of look at this as today we have 2.5 inch, we have 3.5 inch, and we have M.2, right? So we're hoping that we can kind of, in the future, have E3 short, E3 thin and thick, and then M.2, or E1 short as a replacement for M.2. So we're kind of looking if we can get to 3 form factors to replace the 3 form factors we have today and minimize that. Hopefully, maybe we need to go long, E3 long for some specific storage applications. We're trying to maintain that within the E3 short, thick, and get to the capacity we need with the short and the thick. So I think that kind of covers everything that I wanted to cover. Bill, do you want to touch on something?
So basically what I wanted to stress was, up front for E3, we targeted the power levels we believed we needed to saturate a by 4 Gen 3 and or by 4 Gen 4 and a by 2 Gen 5. So, we started out at those power levels of 20 to 40 watts in that range, where E1 was quite a bit lower. We looked at that and it's like, yeah, no, those weren't at the power levels we wanted. So that's one of the reasons we started with E3. Now, from Dell's point of view, we're interested in both the short and the long, mainly because we have a big storage group that shall remain nameless that we have to deal with. As Paul said, on the server side, we're probably, pretty much fine with the E3 short, but we do have a substantial server or storage group that is in New England that really wants the E3 long. Short and long, since they're all the same height, we can easily swap between them. Our servers are, pretty much based on the traditional 2.5 and 3.5 inch drives that are shipped today. So we have a lot of platforms that we can, pretty much do customizations to put either a short or a long in. We definitely need the short because we do have modular platforms and platforms that are aimed at, the edge that need the shorter chassis depth. So we definitely need the short. But we believe E3 is the way to go. And as Paul pointed out, you can still put 20 of these things in a 1U and still get the thermal benefits because your backplane doesn't take up the entire chassis. You can do, lots of big holes in these things and get a lot of airflow. The other reason, also, as this picture shows, we can scale from a by 4 to a by 8 all the way up to a by 16 in this form factor, which is really good for accelerators. And, with storage class memory coming in, we may need that additional bandwidth in a device. So we're between, it's one of the few things Dell and HP really agree on, but we definitely agree on this one. So.
To get back to thermal modeling for fun, in this particular setup in your 20, would you expect the nearest neighbor's effect to affect a vertical stack, or would you expect the full stack?
Probably the vertical.
12 devices.
We believe these guys will have a greater effect than these guys. Yeah. I won't say that. I'll leave that to my thermal engineer. I don't want to get in trouble.
question. Evaluations, 12 drives or
4. Yeah.
Unless you have a 2U activated.
yeah.
No.
So we do think that there'll be
Like in some of these, right, there's not that, there will be
some isolation just due to mechanical activity. There'll probably be, some metal detector somewhere. That'll restrict some amount.
So the other thing is, from Dell's point of view, we probably won't stack 46 of these things across the front of a 2U. I mean, that's a lot of devices in a system.
That kind of breaks this rule, right?
Yeah.
I mean, it's really all about figuring out how much value you really need
Your platform, and then you scale your number of devices to meet that, so that's your minimum cost. You're not running
I mean, really, this is going to be, when you start looking at this shared front end, and you start saying, when you come to the future where we have CXL and Gen Z devices, you're not going to have the whole front bezel space for NVMe anymore.
Right. Right. And also, we are probably past the world of being able to fill up the entire front end of a server with devices. Given the unconstrained TDP ramping of certain processors, we may have to put some big holes in the front of the server just to get enough air to cool the procs and the memory. Actually, it's not so much the processors anymore, it's the memory. The memory is starting to go really high in power. Yes. There's a group in New England that is part of Dell that's looking extremely heavily at that. Yes. There's nothing to say that these things have to plug into the front. They may drop in from the top. Yeah. Yeah. Oh yeah, hot swap is required, and there are. If you look at some of the big data tubs, they are drives that drop in from the top. You slide them out and drop them in. So, yeah, yeah. But then that's why we have the E3 long. Yeah. 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 Sure. Yeah. Yeah, it's all workload driven. Yeah. That is probably true.
Well, I think it depends on which one you're doing. If you do an E3 long, then more. But if you're doing an E3 short,
yeah.
Definitely not. So I think I took it off.
So, is the server guys looking at like E3 long, double wide, triple wide, like Microsoft was proposing?
We're looking at E3 double wide, definitely. That's an E3 thick. We're not necessarily looking at a triple wide.
We're not looking at long double wide.
Yeah.
We think that form factor,
Again, with form factors, you design things sometimes last 10 years, 20 years. So maybe some new use case for 10 years will be opposite today. Today, we don't think that's the use case for go. When you say double wide, you mean
yeah, the E3 thick.
So like the thin versus
the
thick.
Yeah.
I misunderstood. So when I think double wide, I think
guys, I was thinking 2 or 3 thicks as a brick.
So for instance, one of the things that I'm looking at from a platform perspective is not just for storage, but accelerators and other devices. Where I personally like the E3 long because I can fit an E1S in it. I can fit an E1S in a E1L.
Right. Right? Yeah.
Short, I can't take that and put it in there, right?
Yeah.
And if I really want to do accelerators or NICs,
well, we have looked at E3 long thick, mainly because it's roughly the size of a Kim card. Yeah, it's very similar.
A little shorter, actually, by 35 millimeters, which when you look out further generations from now, you don't have as much room.
Yeah.
Yeah.
So there's a lot of work that was done on the GMC consortium to do a whole scalable architecture, right, for form factors.
So E3 was one of those scalable form factors. I forget the XYZs, right, but they're all scalable dimensions of each other. There's an effort right now to move that entire mechanical work group, all the work they developed in Gen Z, over to SFF. So there would be kind of you just dial in whatever you want, and it's all a scalable form factor, so that you could say, if I had to go, do some enormous device that was 3 thick wide, you could do that, and it's all specified with, what your spacing is. And
I'm thinking maybe double wide. To get rid of something that's been around 25.
Right. So there's another form factor that, right, is to replace Kim that Gen Z has done. That's the PEC FF. Are you familiar with that?
Still got some problems.
It's not big enough?
Well, no, it's got the same problems of the PCI bracket. It's got tabs and things sticking out in places you don't want. You can't fit two in a 2U box. You can't, or 2 double wides in a 2U box. You can't fit 2 single wides in a 1U box, right? It's just, to me, the AIC form factor is a leftover from the client world 25 years ago that was brought into the server.
Sure. Yeah.
And that kind of follows on, I think, the storage form factors that we also are evaluating.
Right.
So I guess my question to you guys would be, where do you see the most flexibility, let's say 3 to 4 years from now, out in the 2023 time frame?
Mm-hmm.
Would you see more flexibility in having an E3 long that could go in the front and the back, where you could swap out storage? Maybe I want memory, maybe I want accelerator. But it's hot swap all from the front, and it's all the same length. So I don't have to worry about a short versus a long versus a thick versus all that stuff. Yeah. And you kind of consolidate down and work on form factor.
You can take the E3 short and
put it into an E3 long slot
with a carrier adapter, right? So, I mean, I think the difference is that for us, we have a huge amount of pressure to keep our server designs. Like our customers, when we grow our server design 1/4 of an inch deeper, they yell and scream at us, right? They're like, why did you do that? And so we can't just go and say, hey, magically every single server is going to be a large form factor chassis depth now. So that's like a deal killer. That won't work. So that's why we have to today we have small form factor chassis, large form factor chassis, and that's why we can't really just grow the chassis to say what's the largest one, right?
Can you see that far out, the short 2.5 inch depth?
I don't see it magically growing to be like we can always put a long form factor in there. We get constant pressure to keep that as short as possible.
Drive that from that point of view. Can't afford the reactor depth in our modular platform, and we cannot afford it in our edge platform.
Okay.
Hey, Paul, so I think you've got some of the SSD vendors want to get some reuse out of the E1.S and the E3 storage, and kind of fix that up a little bit. In this type of chassis design, you push E1.S and E3.S.
No. And we really, really pushed hard when we were doing EDSFF to say, guys, please make E1 short smaller. It does not fit in the existing 2.5 inch chassis that is, millions of install base, and we couldn't get that. We couldn't get that. It's like a 8 millimeter difference.
Hey, Paul, this is Jonathan. Are you talking about E1.S or EU3.S?
E1.S.
And
when we remember, Jonathan, when we were trying to get E1.S to be the same depth as E3.S.
Oh yeah, we tried to converge. Yeah, we tried.
We tried to converge there, and we just couldn't.
Yeah.
But based on the bare board or based on the explosion with glass now?
I think you know where I'm driving. A lot of us SSD vendors, we think 2 variants of E3 is probably manageable for what we have.
Yeah, we want to minimize as much as possible. So I think for us, we're looking at saying if we can go with a short, thin, and thick, that for us that covers us. I clearly hear Dell says we still want the long, right? So I've tried. We're working on them. But Yeah, no, I think we hear that loud and clear, right? We're the biggest proponents of that. We want to try and minimize the number that are there.
Hey Paul, for E3, at least for the E3.S, or actually for S.ORL, do you see by 4 dominate? Is there a by 8 version that you see affinity for a certain version of E3?
I think for an NVMe SSD, that by 4 is going to be dominant, right? I mean, I think obviously if we get to Gen 5, we'll have a lot of SSDs that really are only designed for by 2 throughput. They may still be by 4 PHYs, but I think as we get to the other devices, right, when we get beyond NVMe, storage class memory, CXL, those devices, I think that's where I'm going to see the by 8 as more meaningful. And maybe even we've done some SCM modeling where we see that those could take advantage of even up to Gen 5 by 16. So
the other thing.
Right. So if we're planning, the drive can be by 4, but I mean the slot that we make in the system has to be a by 4 or by 8 in general, right? So do you see typically the slots will be by 4 slots?
Yeah. Well, so the slots will be by 4 connectors, I would say, and then I think plumbing. So I think plumbing is the ability, and I think I've talked about this before, where you can always route 1, 2, or 4 lanes to the drive. So the slots may support a 4-lane connection, and it depends on how you cable it up, how many lanes you dedicate over there. So I think it's a little bit where you can make it to where it's customer flexible. But I do think most of the backplanes will have a by 4 connector, and then it depends on how many high speed you need, whether you do that with a dedicated backplane or you have a hybrid backplane.
Yeah, and from Dell's point of view, we believe it's going to be by 4 because we still have a need for a dual ported drive for our storage group. So it'll be 2 by 2s.
Yeah, that's part of that's the questions I've heard is there's a debate of 4 by 4 versus 2 by 2 is one part, and it seemed like the long was more prone to you might want to by 8 versus so the short maybe is by 4.
From the storage group's point of view, we're not really considering 2 by 4s. 2 by 2s work fine for us. For storage class memory, we are definitely looking at a single by 8.
Yeah, that's what I meant. 2 by 4. Yep. Okay.
Yeah.
When we talk about modularity, one of the things I observed that I don't think SSD is used for a long time is that the things looking at 600 watts per plate. I don't see anything we've talked about that's going to come close to what we're doing unless you're going to build an 8 of those.
Yeah.
Yeah.
No. But, remember in the early days, we thought terabyte drives were ludicrous too.
No one will ever use that much power.
Yeah. So. Any other questions? 1.8.
How does what is your impedance budget? Well, impedance budget with the
I do not have any charts.
Well, I didn't bring any thermal stuff today, so
yeah. We were told to keep it to 1, maybe 2 slides.
Is it synonymous with what you've done in the past, or is it
No. We actually get much better thermals with this setup than we did with the U.2s. But I don't have the data with me.
I think it's primarily because when you look at the gaps compared to the device-to-device gaps, compared to how much other space you have in the back, we were actually more constrained in the back with 2.5-inch drives than we were
the down. So this is where you're going a lot of
Yep.
Now, because these are in the front, assuming that these are probably not your bottleneck now, like CPU or something?
Well, the main difference is just that our backplane, was mostly blocked when it was 2.5-inch drive. The connectors are so much bigger, and so that we basically just have a lot more blockage right at the backplane level, whereas now we don't have that blockage.
Okay. So in other words, you're able to hit a sweet spot in the fan.
Yeah. Yeah. Well, okay, given these racks are 19 inches wide, okay, if you look at PCIe Gen 5, you have a 36 dB total SI loss budget. Now, Intel graciously eats half of that with the processor and package, so that leaves you 18 dB left, okay? So you now have to go from the processor out to, depending, if you're using say a SAIL connector, you go from the processor out to the SAIL connector, and then you go, through that connector onto the drive and through the package loss of the controller. Package loss on the controller is pretty small. So let's say the drive eats up about 6 dB of your loss. So you're now down to 12 dB. The problem is that's a really long trace run you have to run all the way from the package or all the way from the proc out to your farthest, drive out on the end. You probably can't do that with regular traces. Yeah.
Lots of cables. Are you doing all? Talk the processor, which why you want to about 5 inches.
You can do that.
Sure.
Okay.
You have
I would be surprised if you can keep that within 5 inches from the proc through the dim field. And do you have fans in this thing? Yeah. Well, we put the NICs, OCP NICs in the back. We don't put them in the front. Yeah.
I think I would probably say it totally depends on how you design it.
Yeah. Yeah.
I think in some cases, for us, the way we design ours, when we look at them with those, it's easier for us to do backlinks,
Yeah.
and get much better SI over the cable than having to, pay a penalty for a long time.
Yeah, absolutely.
Yeah. Yes. Yeah. Yeah. Yep. No, I don't think so.
A lot of the vendors are looking at direct wires that shouldn't alleviate
Yep. Yeah, we're playing all kinds of SI games. Yeah. Yeah, and one of the problems we're having is if you go look at the Gen 5 the PCI SIG spec, the only model they call out is the Chem model, and that doesn't work for us. So we've been trying to figure out how to get a more storage-friendly SI model pushed into the SIG.
Sure.
Yes.
So I would admit I always thought there would be a mid-plane switch on this sort of just to make it work, in which case, just talk of signal integrity is kind of a non-issue, right? It's localized.
Yeah. Yeah. Oh yeah, if you put a switch in it, it becomes much easier, mainly because the package loss in a switch is nowhere near as high as CPU. Yeah, so we don't want switches.
We don't want to add switches unless we
Yeah.
have to have retimers unless we absolutely have to.
Yeah.
We're trying to do everything, as much as we can. If you're doing it direct connect, then that's really the challenge, right? If we're doing it with a triangulation controller, it's easy.
Yeah. Yeah.
That's right. That's built in right
Yep.
cables, right? So.
That's it.
I'm sure there'll be more questions later. All right, how about we take an 8-minute break and we'll resume here at 3 o'clock? And then NGD and Western Digital, you had some presentations. We'll start with those.
Good to see you. Big call so far.
Okay. Yeah, good to see you.
It's much different when you care to your volume stuff.
All right.
I know. Planning for our Virginia and
I'm sort of interested in understanding
that's like going up again. Oh, okay. Yeah, that's like that.
So the long or the short currently is at 20. We're trying to push it to 25 to 1, and the long is around F2. It's kind of like what they were saying.
Oh, yeah.
We can do it. I'm not particularly interested in that. That's not my but we figure we need about 20 watts to saturate it. Roughly. When you perceive
We made a little odd decision. So I think if you look at it as I think our replication probably stellar compared to most others. This is QEI. I mean, yeah, and QEI because power was managed. So the guys reached Microsoft and stuff like that.
On the page, on the front page,
I think that's
Oh, sorry.
Like, really,
what happens is when you just drop. That really helps.
By the time we're in.
So we want to see if that advantage can come out, if, higher capacity, higher performance. So we move on to like a challenge.
But it's not hardware. So you are.
Extraordinary language. All of our drives.
And then you can rebuild it, it gets drafted. If you read back the data, we don't know, there's some bit of all wrong, we just don't know where it is. So if you have the you'll build your visual back, check them in, where it is. Take that part.
We've done that with other Flash drives.
And next year, what we're going to do
when they're wondering why we're performing this work.
We did.
Right, especially when you're building. But their whole, their thing is really good.
Yeah.
Same with the Liberty, so I don't know.
Yeah, I was just looking at the
Probably, I don't think 50-50, so it's better like 75-25. But he would know. Yeah, I'll dig it up. I'll get it to you. Going anywhere for the holidays?
It's like a
Thanksgiving in town like that.
you're gonna do it? So we're like an H.
I actually like it. Yeah. It's nice to do. I mean, not only so you know, I kind of like the work. It gives me a chance to but he was out here. But well, I mean, that was right. So let me. He does okay. Yeah, his name begins with a P, but he now does a lot more other business stuff.
So there's pretty good chance of having
Yeah, I know. Well, we all know that. We were hoping you guys were going to be no to 10. We did. We were hoping. Yeah, we're really right. That's all right. You can really. I think we know around. Yeah, we're
coming up.
Sorry, I apologize. I just wanted to improve.
I
know that's good. Yeah. And then she got different company. That's not hard to do. I get it. You both have work. Oh yeah.
Okay.
You have
Yeah, I think I might have a use. Fun.
Yeah, I am. Yeah. Oh. Yeah. I'm really. What are you doing? I'm a platform architect in the Server Advanced Engineering Group. Okay. And so I've been attending. So I'm working on Constraint. And I'm wondering, I know like that thing right. Like a week. Some of them. Okay. Yeah. Well, I'll look for you. That's except for Jimmy Pike. Oh, Jimmy. Well, see, Jimmy and I worked together back in Columbus. Oh, okay. Yeah, he is quite the character. I
I'm in no particular rush. He said my name first. I'm not sure if that was on purpose or not, or if it was alphabetical.
You ever pig and mud and some other things? If you ever want to have fun, ask him about his ARM-based server.
Okay.
He has his. We had experimented with doing an ARM-based server, so they built up this one, and he
All right, for everyone in the room, we're about to get started.
Everyone
grab your seats.
So the
we're gonna grab the stragglers outside, and then we'll get going.
The guys built a little case to put this thing higher than I want, and then shut it. If you look out. So he was going to this conference. He goes through TSA. They X-ray his case, and they say we need to look inside of that. It doesn't make sense to us. So he brings it over and opens it up, and as soon as he opened it up, he says, "Yeah, this is going to be a problem because here's this box with all this electronics." And it has two labels at the top. It says ARM 1, ARM 2. He said as soon as they looked at that, they shut the case and they said, "You need to come with us." Oh, no.
I am logged in.
Page one or the wall? Every time I see this, I think it needs to be a different one. I don't even know how to we can just entry 25.
So I have to.
You need to download the GoToMeeting installer.
Oh, great.
So if you want to do that, then we'll let Scott go first.
Okay, I guess so.
Scott, are you ready? Yeah. All right. Let me make sure.
Another one.
Yeah.
I'm on there, I promise.
Oh.
So you're still actually watching.
Oh, man.
A long that Friday. Okay.
Oh, because I have to be an organizer?
Yeah, I am.
You're not so organized.
Yeah, I'm not shown as organizer anymore. All right.
Is the room classified as an organizer?
And if you touch the computer, all right. Thank you. Sure. I got it.
All right, everybody else, let's get going. We're kicking off right now.
That's weird. How did you get?
Yeah, no, I get the motive. So it may not have been you, Dave, but you.
Actually, it's working.
Good. I just said share it. And let you do it. That's dangerous. There we go. Sure. Oh, no, I used to do that. Yeah.
All right. So my name's Scott Shadley. I'm with NGD Systems. We're doing a little spin on technology. For those that don't know us, we're adding some ARM cores into our controller. What we've done is this is a picture of my cased EDSFF. I have an uncased one up front if people want to take a look at it. Our focus for the most part in this work has been on the high capacity side of things. So the flow rates on these particular slides were not exactly what I asked my engineers for, so they're a little higher than we've been talking. So I appreciate the feedback on that. But basically what I wanted to show was just some ideas of this is what we've got as far as our particular product today. It's not looking at needing or requiring any kind of an external heat sink to be able to maintain the proper airflow. The top left is our 16 terabyte version, which has no power loss protection but can support that capacity point. And then the graphical one below, which was actually used for these thermal models, is a 12 terabyte, which has full componentry and power loss protection. So either one of them fit within this construct of this particular case design. The two holes on the bottom right represent where the latch would go, for example. So this first one is showing a 200 LFM flow rate. Our drives are running at 12 watts for all of our simulations. That, for our particular solution, is max power draw for this particular drive. We're not looking for the million IOP type solution, but more of the overall aggregate throughput, kind of like what Paul and Bill presented about the fact that when you put multiple drives in a system, you end up with IO bound anyway. And so this one's 100% right, and as you can see here, the controller represents the hottest component on this. We would be using TIM within the constructs of the case to help with that airflow and transmission rate. So This particular component here in front is where the regulator was placed, and it didn't have TIM put on it for this flow therm, and that happens to show that without TIM, it sits at about 110, 118 degrees, but majority of the components sit well below the 90-degree rate. Thermal interface material to allow heat conduction from the components to the actual case.
Is this a 9.5 form factor?
Yes. So this is E1 short 9.5 symmetrical design, no external heatsink. No asymmetrical heatsink required. And then the second one is just the same exact thing, but even faster airflow, which may be less relevant to some of the concepts of the room that we've been talking about, slowing things down. But again, just shows a different version of that and where that hotspot continues to exist. Our controller, of course, being the second hottest component, but we're not seeing, I had them rerun it. I don't have the slide with me, but I had them run it at 100 LFM for the simulation, and there's still no issues with heat transference for this particular design. And I'll be able to post probably by the end of November results in the new guidelines that were sent out by Jason and team earlier. So,
Known for the pitch of this at that LFM.
The between drive pitch, it's at 2 millimeters in this particular case.
So 2 millimeters gap.
Yeah. Does this what? This the way it's positioned is showing that it's just showing the XYZ. It's effectively the vertical insertion. It's not laying flat against the motherboard.
Okay, but with this laid flat against the motherboard,
it could, yes.
And have you run that simulation and decreased the main gap between the bottom of the circle?
We did a simulation run similar to that of an M.2 connector in the distance there, but I don't have that data in this particular data. So.
And just to clarify, your LFM is channel LFM or approach LFM?
This is approach.
Okay, so very high channel LFM.
He ran
you're about 1600 LFM.
Yeah.
Okay.
And there's some work to do on it. I apologize. I was hoping for a slightly more appropriate pictures. I just wanted to show the data.
Yeah. Do you also account for drive heating from the previous one? Does it include symmetry, or do you include the delta T from the next one over? Because if you have a 2 millimeter gap, then you've got heat from one drive filling up that one gap, but in reality, you'd also have the shared heat from the other drive.
There is some work done on that. It's not shown in here by any stretch. We have done some data work on that. Again, since we kind of have a hot side and a cool side, if you will, the heat transference tends to be fairly consistent across the array.
Okay, thank you.
Yes.
Have you looked forward 2 or 3 generations and you're operating how are you expecting then?
We are seeing that we'll probably see power continue to go up. For our particular focus, again, capacity versus performance, we're not as worried about the overall power consumption from that perspective because our performance will be aggregate for the box, not per drive.
Okay, so if we find commonality somewhere between 9.5 and 15, for example, you should be good to go.
Yeah, we did an example using the 25 for purposes of the data. That I can't show it because it was ugly as far as the results weren't in a positionable point of view, but more than adequate enough. Even if we went to a 15 millimeter, we'd be fine. At this point, we're seeing that for our particular drive doesn't even need over the symmetrical version. So pretty easy, pretty straightforward. Just wanted to share it. We'll get it posted out onto the wiki as well, along with the other presentations. And as I get more material, I'll be happy to share it as well. Any other questions? Yes.
Hey Scott, this is Jason. Can you hear me?
Yeah.
You beat Gelden to the question.
All right. So I was just going to say this aligns with the thermal simulation we did on the E1.L. Because we did evaluation with just air card with some rails, simple rails on the outside with no TIM and heat spreader at all. And in airflow cases, pretty much across the normal ASHRAE airflow cases, we could hit 12 watts without any issues. So having the case on and putting the extra heat sink on there, heat spreader, as long as we get the good airflow between drives, this aligns with all the data we've run.
Thank you.
So it's just breaking some of my normal expectations. So being OCD, it bugs me. I normally expect I thought we agreed the airflow is going to be to the connector, not from the connector out. and I expect the SOC to be close to the connector. So maybe your connector is in the wrong place?
Connectors here, controllers here, and airflows from the back to the connector.
Oh, that is the connector.
Yeah, sorry.
Okay, I'm looking at the latch
the connector was at the back.
Okay.
No, that's showing the latch, basically.
Got it.
So for those on the phone, the connector is at the center of page. So it is having the SOC closest to the connector, yes. And the SOC is the hot yellow spot in there. So, and then this, of course, was the one that shows a slightly less airflow from that perspective. But yeah, so the connector is here in front. So airflow is the right direction, maybe a little fast, but it does show some of that data. All right. Are you ready to go? Cool.
I think so. Share screen. Yeah, I turned it off. So you can share screen here.
Okay. So we just wanted to show one slide today. We did a little bit of, we haven't had a ton of time to evaluate the whole new methodology that's been talked about by Microsoft, but we presented some thermal data at FMS, which is represented by the gold curve at the bottom and the blue one at the top. So we presented that data at FMS, which basically said that on the 25 millimeter asymmetric E1.S, we could get up, the 25 millimeter, we were running a little hot. We were closer with the 25 millimeter, but with the 9.5 millimeter, if we took it to 20 watts, we needed a lot more airflow and things like that. So we tried to find where's the sweet spot, like, you were talking about a little bit. And so at 14 millimeters, this is the data that we just simulated. So that's it's just a little bit of data. David, are you still there? If you want to make any comments or see if David Wright was on the line before, so I'm asking you those questions.
Yeah, I'm still here.
Yeah. Okay. So, any questions or? You have a question, David?
I don't have a question, but I can't hear who's speaking.
Oh, sorry. I'm not much of a shouter. Is this through channel airflow or approach?
This is approach. Yeah, as was discussed before, all of the different approach speed, pressure head, and local speed, those are all interrelated. So requesting for one is going to affect all of the others. So sometimes if we want, as a system level designer, or between system level design and device level design, it's always good to have a good communication between all three of those variables.
And this is just for a single SSD?
This actually is considering multiple SSDs in line. So this is considering a center SSD with adjacents on either side in a stack of 5.
Any other questions? Ross, you had a?
No, my question got answered.
So, short and sweet, I guess. Yeah. We'll post the slide.
So, Dave, have you guys done any work to look between 3 and 5, and if 3 is enough? For the cross-seating effect? Yeah.
I seriously doubt it. David, you said you did the sim with 3 cards, right? So not 5?
It was a stack of 5.
Well, there is a stack of 5.
Okay.
Yeah, the simulation that I ran was with a stack of 5.
Okay.
I don't think we had that question in mind, but that's what we were.
Just to clarify, what are we seeking between the 3 and 5? What's the answer we seek?
Go ahead.
What the difference is between overall power or overall airflow?
Well, the discussion was to if you have to hit the worst case hotspot in the middle, do we need to simulate with 3 drives or 5 drives? You know, kind of analogous to system to SI problems where we need to do, you know,
nearest neighbor and far end,
to get to 5 wires.
Yeah, my experience is that the middle drive is going to be pretty much, there's not going to be a significant difference between a 3 stack and a 5 stack. The major differences happen on the edge. The ones that are going to be all the way on the extreme of the stack that doesn't have an adjacent drive on one side.
Yeah, that's what our simulation did. So, where are you pulling this airflow number from between the 3 and 5? Where are you reading the CFM from? Is that the domain, or are you taking the most restrictive channel and reporting the airflow from that region?
No, that's from the inlet domain. So if I take a drive and I calculate the cross-sectional area of one drive, and that's what the CFM would be for the inlet.
Oh, got it. Yeah, no, I understand that. But you're just taking this from your inlet velocity and then your area. Okay.
Exactly.
Out of curiosity, what tool did you use to run the analysis?
This is through flow simulation, SolidWorks.
Oh, Therm XT. Or Therm. Okay. XT or Therm.
Right.
What was your pitch on the 9.5?
XT or Therm?
So there's Therm and then there's Therm XT.
Yeah, which one?
Well, it wasn't Therm. I was using SolidWorks flow simulation.
Yeah, just clarify, what's your pitch on the 9.5 you used?
12.5.
Okay.
Or it might have been less. I have to recall that information.
And were you determining the CFM as a function of the enclosure hotspot? In other words, the maximum ergonomic temperature may be constrained?
No, it's a case temperature, it's ADC scenario.
Okay, so your ADC is limited.
No, I think he's assuming he's. Hey, David, this is Anthony. Your second bullet says SSD case temp exceeds ADC in these scenarios. So SSD case temp you're not using as your limiter. So I'm assuming that you have another device in there, be it the media, probably the media that's being your limiter.
Yes, that is correct. There's a device inside as the limiting device and not the case itself.
Okay. And then
so
sorry, go ahead.
Expand that what we discovered is that keeping the case temperatures at 80 or lower sometimes that limits how much performance we can get out of our components internally.
Understood. Also on I guess the same question on the pitch for the 14 millimeter, is that assuming 14 on 16 millimeter pitch?
No, so earlier, 1 more millimeter in addition, so 15 millimeter pitch. And that's just 1 millimeter less than what Microsoft was proposing earlier today.
Okay, but was that a solid block or was that with fins?
With fins.
Okay, that makes sense.
And is that symmetric or is that asymmetric?
Asymmetric for the 14 millimeter. So it looks like the 25 millimeter just with 14 millimeter height.
Did you monitor which media had the lowest margin?
Yes.
Which component?
Yeah, well, was it the top side or?
The RAM, the NAND.
Well, for the NAND,
yeah,
you said.
Yeah.
Was it on the
we
top
monitored the
side or
NAND.
and was the restrictive NAND on the top or bottom side?
On the bottom side. It was
Okay,
on the
good.
side without the fins.
Yep. Okay. Good. We have the same thing.
Yeah.
Okay. Consistent. Good. All right. Any other questions? Otherwise, I'll. Yep. Okay. Thanks, David.
You're welcome.
We just got this data like 24 hours ago, so better to have him talk to it than me.
So, all right. So, if we have two more things I want to make sure we cover today. So, I want to have a deeper discussion on E1 and E3. Specifically, it sounds like we're not going to have convergence on E1 and E3. While, it's a little bit unfortunate in widths and depths, it sounds like there may not be flexibility. However, when we talk about E1, I think we should make sure that we leave this room with an alignment on what to do with E1. So, consumers of E1, those of us who are interested in it, after you see some of this data, our proposal, at least from Microsoft's side, somewhere in that 12 to 15 millimeter thickness seems to make sense for us. We propose that we continue these conversations and simulations, make sure that we're all heading in the right direction. Can we all converge on a specific width, meeting the needs of both the end device consumers, so many of us hyperscalers and OEMs that might consume it, as well as all the device creators. So if we're simulating your current product now, that's going to be short-sighted. We want to make sure that we're simulating at least 2 generations out. We don't want a form factor that's going to be challenging moving forward. So let's deep dive in that a little bit more, and also in a little bit later, if Whitney's available in a few minutes, we want to talk about what would an accelerator look like in an E1. Is it E1S, E1L, E3, something different? I had shown some ideas when we kicked it off earlier this afternoon, but maybe we'll dig a little bit deeper in that. So does anybody else have data? Anyone have any recommendations and thoughts on that 12 to 15? Any boundary conditions we think we should be setting and targeting, at least for discussion now? Is this something that people need time to take back and think through?
It certainly does seem like everyone's getting limited by the back plate or the bottom without fins, which makes the symmetric, asymmetric, possibly moving that boundary around.
So why you said, okay, so in case anyone didn't hear, you're saying that the asymmetric may be bottlenecking us on the side that doesn't have fins.
Yeah.
So I haven't heard that yet. Is this?
I just heard that from Brandon and from Dave. That both sides, the back side is the hot limiting side.
Only when it's against the sidewall, though, right? Oh, all the time. The NAND. Okay.
Because it's basically you have a flat plate and you can't get the boundary layer area on a flat plate. It's basically linear, and then doesn't matter whether you're against the ruler.
Yeah.
So just simply put, it's pipe flow on the flat side, and so you basically get half the boundary layer development, and you may not actually reach turbulence when you do your Reynolds calculation. So
is allocating 1 millimeter for fins enough for any significant cooling?
Yeah, I mean, you're drastically increasing your area, right? If you go look at the fin efficiency calculation and correlate that to overall area of the drive. The only limitation there is that you may have to start investigating custom connectors, because for coplanar oriented E1.Ss, you may not have the height to clear the motherboard.
So we could probably do it. Force us to a straddle mount, which is probably okay. But I think this is on our backlog right now, so we actually have looked at a semi-symmetrical, where you have larger fins on the primary side of the controller. We've talked about smaller fins on the secondary side.
Anything that moves towards symmetry would help, right?
Well, I actually don't think it would, though. I would argue we should not be targeting symmetrical, because as soon as you say symmetrical, now you're putting the secondary surface as having the same thermal capabilities as the primary. But I have not seen any examples where you're going to have equal power on both sides. Do you see a use case for that?
Well, maybe not equal. I should ask David, but
Well, so you're just balancing your heat flux on either side, right? So right now you have basically zero area outside of the flat plate, so your heat flux is very high, and so that's why your NAND temperature is very high on the opposing side. But if you go from 3 millimeter fins to 1.5 on either side, you may be knocking off the balance between the controller side where there's a lot of power, and you're reducing the area, so you're increasing the heat flux, and now that becomes your limiting side. So I think, so Jason's point is probably just finding the healthy balance of fin distribution between top and bottom.
Well, that's what I thought I said. Yeah.
Okay. Sorry.
Is shifting the balance a little bit, not necessarily going all the way.
I think you implied that there's a mechanical concern with having. So if you want to stick it on top, so it's great. We have a whiteboard. Sorry for people on the call who want to see this. We can set this out. So if we were to do a kind of a coplanar design, so the connector is in this plane here. If you want to put it above a motherboard, so take a side view, add a connector that runs up, put a device on top, essentially. But if you start growing it, you're probably looking at more of a straddle mount where you have a connector either coplanar with the board or slightly above, and then your device can go above and below. That's kind of what Brandon is going at. So the secondary side is facing down, primary side facing up. If you grow the secondary too far, you're going to start to hit the bottom piece of the terminal, where one of your two gaskets depends on your standoff of your motherboard. So there's only so much you'll be able to grow and make it a useful form factor in a horizontal application. This won't affect
And probably growing your connector, do you know what the SI implications of that would be? Or?
I don't think we grow the connector, I think we just shift where it goes.
Oh, okay.
And so either keep it just above the motherboard or straddle.
Probably your connectors can block airflow. Your connector's going to block airflow in the back. Your connector's going to block airflow on the backside. So then it becomes useless.
Depends on how high the connector is. I don't know. The T1002, the exact height.
So for the models that people have already done where they've shown that the non-fin side is the limiting factor, how far of a limiting factor is it? Like, is it fairly close, or do we kind of get to the point where we say we do need some fins on the other side to get those to be a little closer so that the thermal top and bottom are not so spread apart from a limiting factor perspective?
Yeah, that's an excellent question. So I think you missed the beginning. We showed our data with current gen, but I think what you're getting at is when you get to Gen 2 and Gen 3, when the NAND is consuming a lot more power, I think we're looking for all the SSD vendors, how much higher is that power going to go? Is your T case going to start dropping? And what considerations do we as system designers need to think about? Because you build a device, we want to make sure we can actually cool it. How far is that secondary side being a limiting factor? So that's an excellent question. I think, how do we get to, I know it's going to be hard if we have future roadmaps. No one wants to expose what they're thinking, where they're going. But we have to have enough data that we build a form factor that will accommodate it. It can't be vendor specific.
So for 9.5, it was 1 to 2 C difference between the limiting NAND and then the next coolest NAND, which translates into 7% or 6% difference. But then when you consider airflow, that becomes a cubic result in terms of fan power. So it's actually a pretty significant difference.
So one thing on the 9.5, I'm going back through what was written in the spec. And one of the things is that, we're calling out both sides being about approximately 3.9 millimeters thick off the motherboard. I mean, if it was perfectly symmetrical, so you count 2 millimeters for components, that gives you 1.965 to play with for sheet. If you wanted to add very, very small fins, for instance, within the 9.5, you could, or you could expand those out. There's nothing that says in the current definition of the 9.5 that you couldn't have a little bit of indents there. I don't think we said it had to be perfectly. It's drawn like that today, but that doesn't mean it necessarily needs to be like that for future generations.
So I guess the only question is, so at least looking at your sample, you're using both sides of the board. I don't know how you would get fins on the secondary side within the 9.5.
Well, this is what I'm asking. This is what I'm asking though. Is that if you go all the way to 15, maybe instead of going all the way to 15, maybe you go to 13, but you got slightly smaller fins on both sides. or you go to 11 and go slightly smaller. So you get that. So you get the symmetrical balancing that I think all the device vendors are looking for, such that you can get such that there's a 0% deviance or variance.
Yeah, I don't disagree. It's just I don't think it's analysis that we've run because I think we all focused on asymmetric.
No,
last minute.
You're saying
but I think it's worth looking at.
I think that's an excellent idea. So I think, how are we going to do this, though? Because everyone's controller power is going to be different. That's going to influence the primary side. NAND will all be different. I don't know how different it's going to be this generation, next generation, 2 generations out. How are we going to have this central repository of data to help scope this, unless we just simulate on our own, everyone comes back, and we use your exact same methodology, and for our product, we use X on the primary and Z on the secondary. Sorry, Bill, did you have a comment?
I will in a sec.
Just 1 second. So, does anyone have any ideas how we're going to do this? Because we have consumers and we have competitors building product. I know sharing some of this data can be incredibly challenging, but we're all incentivized to find the right dimensions on both sides.
Well, I know controller power is going up, but I don't think NAND power is exactly not. I think NAND power is also going to go up at least a bit because to get that throughput out, you're either having to increase your back-end NAND frequency, or you're having to increase the number of channels going to the NAND. There's a lot of trade-offs there that are happening. So I don't think the NAND power is exactly going to stay flat and it's just going to be the ASIC power. I think everything's going to go up uniformly.
Exactly.
So then my assumption would be then that you would have that, and this is a bad assumption, but my first order assumption would be media will always be your limiter.
We've seen that as well in our simulation. But again, everyone's NAND may be slightly different. Someone may have more layers, higher power. This form factor then limits someone's innovation.
So actually more layers would be worse because then you'd be conducting more heat into the NAND. So I know there's somebody in our org that's looking at disconnecting ground planes. And trust me, I know it's a SI nightmare, but it was an idea that was tossed out into the wild because we know that. So we've done some studies to keep the SoC controller constant, and then keep the NAND constant in terms of workloads and power contribution to see what the influence of the SoC latent heat is on the NAND, and we know that it contributes even at idle around 3C. So unless there's some wildly different trace design or board layout design that comes out to decouple, then I agree with your statement that they're going to scale proportionally as the SoC and NAND workloads increase. So I don't think it'll be a concern unless you plan on redesigning a board.
Fair. I think that's going to be device dependent. So maybe a proposal. I know we've had a lot of conversation on how do we model the thermals. What's the methodology? If we can align on methodology without sharing, the actual underlying data, every vendor could take the PCBs already defined, primary and secondary. Maybe we set targets of maybe these fins are 5 millimeters and that's 3 millimeters. Have a starting point that maybe seems to make sense. Then every vendor can go out and say, look, I'm looking hopefully 5, that's a bit far, 3 generations out. Sorry, I was getting a little ambitious. And as long as you can cool it, great. Or you'll come back and say, look, for us to be competitive, our primary needs to have X amount of fin real estate, and our secondary needs Y. And at least we can correlate that, because then you're not exposing any of your IP, you're not exposing your roadmap controller or NAND, and that at least levels the playing field on how do we have this conversation. And maybe we'll come back and we'll see that the primary side, everyone agrees, is going to be 5 millimeter fins. Secondary side, maybe it ranges from 1 to 3. And then if there's an outlier of 3, maybe push back a little bit more. But if not, maybe that's the valid form factor. So I think Paul's been raising his hand.
I was just going to start something else, just, thinking out loud here is, we have a 13 millimeter pitch. We have a 9.5 millimeter drive. 12.5 millimeter pitch. Do we care? I think, basically we're trying to find a solution that goes in there. We say the 9.5 is easy to understand because we always have a gap there, and we know what that gap means as far as the flow work to go through an impedance. But if we found a way to utilize the volume where you have equal impedance, but you have a better thermal solution, that you have enough space between that
drive in the next one that you don't have collisions, is that not a win to utilize the volume? Or is there other considerations that we're not thinking of in that statement?
I think there will be system consideration. So especially in systems that may be going 10, 20, 30 drives wide, there's probably a structural support somewhere, so you can't assume a completely open. Okay. So I think there will. And if anyone else disagrees with that from a system design standpoint, that would be the perfect time.
So what are you, roughly how wide do you think these drives need to be to hit your power target?
So the data that we looked at showed us somewhere between 12 and 15 millimeters. But that's assuming an async with, fins on one side only. And we've only been looking at current generation kind of power distribution. That distribution shifts over time. And the NAND gets, I think we were assuming like 2x.
I'm confused, right? We're getting multiple differences.
Yeah, okay, sorry, let's go back. That's why in mind.
So a quick question. So your thickness of your drive is 5.9 underneath that asymmetric heatsink? Is that the assumption?
Sorry, one more time?
So the drive itself, right, there's a maximum thickness currently of the card. It's 5.9 millimeters. And then you add the 12 or the 15 or the 25 asymmetric and so on. So is that sort of where it's definitely a block of just, after that there's components and so on versus heatsink, metal area?
Oh, so what we did, we took a 9.5 enclosure, so it's got the thickness for the 9.5, an example 9.5 inch enclosure, 9.5 millimeter, sorry. We only grew fins on the primary side, so when we're saying 15, that's taking a 9.5 and adding 5.5 millimeter fins on the primary side only. So let me go back to the width, because I know it's a little confusing. So when I'm saying width here, device width, that was pitch, and this is gap.
But when you're saying width, I really call that kind of the thickness of the device.
Correct. It is probably more accurate to be thickness.
I was trying to understand when you were saying the height,
Yeah, it's tough because when you're looking vertically, it looks wide. But you're right, if it's in a horizontal application,
that's why I was always saying, you switched me, because when you were talking Coplanar with the system board.
So maybe it's better, instead of saying width, we say thickness.
So what I'm struggling with right now is, what's the purpose of switching from U.2 to another form factor, like E1S? Ideally, you would get more capacity because you get more devices, right? Or there's got to be a reason to do this.
So for us, we care about 1U platforms at the moment. That's kind of where we're designing around. U.2 and a 1U means you're going to be stacking them vertically.
Yeah.
It means you're going to have a backplane or a cabled assembly. We prefer not to do that.
So you are willing to switch from a U.2 to an E1S just for thermals? No.
Not just for thermals. There are other design characteristics that are important to us. So, for example, maybe it's embedded inside the system or front load. We really care about front load. That's important to us.
Okay.
And having a number of channels of SSDs allows us, if we have failures, allows better configurability. So U.2 is not a bad format.
Yeah, I was thinking, if you go to a 15 millimeter pitch, then your capacity points are virtually identical to U.2.
Different design, though. So now we can put them vertically, put them off in some area of the platform.
What is the thermals of U.2 at 25 watts?
This is pretty good for U.2. It's very large.
Yeah.
But take for an example, maybe we need a boot device or we need a 1 or 2 terabyte.
Okay.
So that E1S takes up a lot less real estate. So U.2, if you're really going for bulk capacity, you're going to pack them deep, then that could certainly work. But for our use case, if we needed 2 to 4, maybe in some platforms, E1S takes a much smaller.
You really need 20 watts then for those devices. You said boot and other things.
Imagine a caching device, something could take very high sequential writes and reads. And then
but for something that needs really high sequential writes, you're probably going to need more than 20 watts.
Depending on the
if you're using that as a cache.
You do flash. With me and flash.
Yeah.
Right?
Yeah. And this is more conducive to things like storage class memory over time.
I'm just trying to figure out what's the point in switching.
So today we use boot and caching devices in the M.2 form factor.
Yeah.
We want to get away from that.
Yeah.
Putting a few U.2s takes up a lot of space in our system. So we're trying to go push on the density.
Yeah, but it's not it depends on
the number of devices you need.
Yeah.
if we
not
need
a
4
density.
devices or 3 devices.
It's not an overall system density play because at 15 millimeters, you don't have any benefit over U.2 from a system point of view. You're looking at, you want more smaller devices.
In our use case, yes. I'm assuming there are other systems that have other reasons to consume E1.
You may want to prioritize other components too. So if we do have smaller components downstream, downstream,
and they tend to have an area maybe 1/4 the width of the server, and so that's when we would start prioritizing E1 over U.2.
Yeah, and the capacity, the density is also not just capacity, right? It's performance as well, right? So larger number of devices, you get total IOPS higher than if you had 10 U.2s or something like that. Right?
Yeah, you want more smaller devices.
Exactly.
But it certainly does seem like, for our modeling purposes, the E1 short and long, we want to look at that model, but we need it changed a little bit for E3. And I would hope we end up with the E3 common methodology also.
Yeah. You're doing the simulation?
Yeah.
Yeah, absolutely. The tough part is going to be system dependent. So in our case, we're looking at them stacked up vertically. Nothing above or below, 'cause it's a 1U. And the E3, there's a horizontal and a vertical application, so it's a little more complicated.
Did you just develop a spec for the orientation?
Well, I would hope the system guys would do that, as opposed to us SSD guys doing it.
I think that was your question earlier, the vertical column and the horizontal. If it's vertical only, it looks just like the same methodology we showed earlier.
Yeah.
But if it's vertical and the horizontal, so you have 2 planes, then you're into a 2D matrix versus a linear. Yeah. So does this seem reasonable, at least this approach maybe? Primary and secondary in the PCB, we know the PCB thickness. Does it seem reasonable for us to ask, the device creators, let's work on the spec a little bit more and how we do the thermal simulation before we go off and run them. So if we have 5 or 6 simulations, all done differently, that data is not going to be valid. If we can all agree on how we simulate, there's still going to be margin of error, but they should be substantially closer. So we all agree that's a good path to do, and then maybe we'll spend the next couple weeks over the mailing list if we need more calls, another in person, lock down the methodology, get us all on the same page, and then run that simulation.
So would you have the same methodology if they were vertical versus horizontal?
I believe it would apply the same way as long as they're all linear. Is that correct?
So is it worth having a chapter on vertical and a chapter on horizontal and various parameters get adjusted or whatever in the methodology? In other words, kill 2 birds with 1 stone.
Yeah, I think the hardest part, at least for U.2, is figuring out what the spatial constraint would be. So, I mean, for 1U, we could set a spatial constraint, but for 1U horizontal, but then for 1U or 2U vertical, I think that's where it becomes a challenge, right? I guess we could use 3 drives.
Yeah, I mean, the whole thing was a domain with just 3 or 5 drives. Didn't really, talk about the system level. If you did 3 or 5 drives vertical, 3 or 5 drives horizontal, then you got a methodology and you cover both. I don't know, just a thought.
Well, so I think for 1U, it's how many drives did you have? 4 in the front? 4. Yeah, so maybe for 1U horizontal, we use 4, and 1U vertical, we could use 5.
Whatever.
That's
just trying to cover both, that's all. Whatever the parameters need to get adjusted for each model, fine. But just really or each approach, fine. All I was really trying to get at is, I would think one would be, the first one's going to be like 80% of the effort, and the second one's going to be like 20%, right? You're just changing some parameters in the methodology.
Yep, agreed.
So it seems like we have alignment, at least for how we go and actually start defining the thermal. So Is everybody here registered on the storage mailing list? Raise your hand if you actually are on the mailing list right now, which means you've seen all the communications from me. Barely over half, and on the phone I can't see your hands, but hopefully everyone please register. If you search Open Compute Storage, you land on the wiki page on the right-hand side. It says, get involved or join the mailing list. Click that, put your email in, confirm it, and then you'll start getting these emails. I think that's a perfect way to kick off this thermal simulation, consolidation, hopefully. I'm assuming we're going to need another in-person, maybe get all the different thermal teams. I think many of us here are looking at products or systems. This may be more system and thermal domain. Hopefully a smaller group of people sitting around a whiteboard debating how we go about this.
Jason, do you have any timeline of driving some decisions?
So timeline about driving decisions, sooner rather than later. So I can tell you we are building systems on E1S right now. I'm sure others are designing it. We have 3 sample drives sitting here, on the desk today that are already under construction. The sooner the better, because I'm assuming as a device creator, you don't want to have a 9.5 and a 25 and then create this third one. And now you're going to go take off the heat sinks in one, put a new package and resell that. I mean, that's just not conducive. So I would love to see at least alignment on this, so the primary and secondary side fins, the device thickness, not width, by the end of the year. I think that should be a fair target. I don't think we should take longer than that. If we're spending more than 2 months to align on this, we should probably adjust our priorities, because this is a big shift in the industry.
Are we still looking at a 20-watt target, or moving into 25?
And see, I would ask, device creators and the consumers, I think 20 might be a bit low if we're looking forward-looking, maybe in the 25 range, but again, our opinions may be different than others. So I think, again, we need to converge on that, because if 2 companies come in saying 20, 4 come in saying 30, and we build a 20-watt solution, you're either going to sell that for a very short period of time, or you're looking in the double thickness.
I know, and Anthony made a comment on you do have, if you're not giving up the number of drives per rack unit, then you do have the ability to scale by number of drives, then rather than scale by power, then make it bigger. So you can go both directions.
All right, Whitney, you ready to go? All right, so slight change in topic. So in the beginning, in the afternoon, I said, if we're going to put accelerators, we have these different form factors, should we consider trying to align on what we're doing here today? So if we align on thicknesses, what else can we do? So Whitney has graciously offered to talk.
Are you ready? Sorry, you get to hang out. Yeah. Next time.
Hey, I'm Winnie from Facebook. While Jason is setting up the slides, I'll just talk a little bit. So I lead the accelerator hardware system at Facebook. And then I'm also co-leading the OAI group under OCP. In that group, we already contribute a form factor, OAM, if you already know it. And today, I like to talk at accelerator about inference. So here is some information I collected for future inference. So basically, since I was not be able to vote for that, for inference, I see we definitely need more bandwidth. So we are go with by 8 and more speed to have more Pcie bandwidth here. And power-wise, we have a different requirement for the inference accelerator. So I would see in like 10 watts, 20 watt, all the way go up to 70 watt. And while talking about the form factor here, I like to see if we can cover at least like more than 30 watt here, and I'll show more data. And while we're considering the form factor here, one factor here is the ASIC package. So I've been talking to different accelerator vendor, and yes. The ASIC package size varies very differently. So we've seen like 25 by 25, and then all the way go like 40 by 40 something. So if you know a little bit, Facebook, we actually contribute a dual M.2 spec, M.2 dual M spec, which is we are currently working with some of our partners to do the accelerator module, but we do see significant limitation for the M.2, something like the power limitation and also the PCB thickness, right? And also the speed. Moving forward, we'll see like we have some other form factor we can leverage. And definitely, I'm jump to the last bullet there. We want to leverage the flash device slot, for example, to like EDSFF, right? We can leverage the system design. So by design one system that we can either plug in flash device or the accelerator device. And also when we consider the dimension of the accelerator, another factor to consider is the memory bandwidth. So if you are in the accelerator side that the input output bandwidth and also the memory bandwidth, we have a tremendous demand there. So we need a more area to be able to put more memory channel. So today we are designing the dual M.2 module. We'll be able to fit in like 4 channel, and moving forward, we want to see if we can fit more. So by considering all the requirements there, here is the proposal for the E1A. I want to clarify that I'm not proposing a form factor for E1A, but it's a concept here. The concept is to leverage the EDSFF connector and depth. When I say depth is like how deep, like we put in there. And if you are looking at the PCB size, I think we're referring the length here. For example, if we leverage the E1S here, right, the depth here is 111 millimeter, and also by a connector. So these are the 2 areas that we want to definitely to leverage for accelerator. And then regarding to the height, if we plug in vertically like this, regarding to the height, we want to leave this very open and then to be flexible. For example, in the edge side, there are tremendous demand when the 5G is coming, and then for the inference in edge, there are also like a lot of demand there. And then for edge, since the server is really small, and then I think E1S will be a perfect fit to have like a 10 watt-ish accelerator module. And then for the typical like 2U system, right? And then if we have an OCP NIC underneath, and then you have an E1A there, I think we can go up to 50 millimeter, and then to cover about 35 watt. And then regarding to the heatsink or the module thickness here, I think we're flexible. It's really depending on what's your accelerator power, and then we can accommodate to that. And then regarding to some extreme case, like more than, I don't know, like 40, 50, even 70 watt, right? And then we can go all the way up to 76 millimeter to be able to fit in a 2U form factor. So we have a different, flexibility here to go different, since the accelerator vendor, when they come in back and then give the feedback to the accelerator module, like roadmap or trending or whatever they are designing, they have a different power envelope. They have a different thoughts about like how many memory channel to put there, and then what's the ASIC size, for example, right? So we want to keep this flexible. Most important to leverage the by A connector and also the depth of the E1S. So yeah, thank you. Sure, yes.
Would you ever consider going, or do you ever see a need to go beyond a by 8 to a by 16?
I think while we're moving to Gen 5, we don't see, at least like within 3 to 5 years, maybe 3 years, we don't see the need to go beyond that. So one thing for the more memory, when I say memory there, we are talking about the memory channel and capacity, right? So while the training or the inference model getting like bigger and bigger, we want to fit into the module. And then while we're not be able to fit in the module, we have to do the model parallelism and then to split the model into different modules. Then that's the need to go like more, I mean, that's the need for to have a more Pcie bandwidth there. I think for data injection, Gen 4 by 8 it's good now. Yes. Sorry, what's the, yeah.
Let's say you had a platform that was designed for connectors in certain spacing. Did you build a module that plugs into multiple of those connectors, or did you envision just using
one connector? Yeah. For example, if we're leveraging the E1S by 8 connector, right? So that's the connector we're using, and then we can plug in like 20-watt module, 40-watt module, and maybe 10-watt module, like by using the same system. Yes. Oh, that's I think for the thickness, right? The module thickness here, I think is pretty flexible. So the only thing we want to leverage that, for example, on the flash slots, right? And then we want the density. So we will have like many slots there. And then if we go with this system with the accelerator module, then we may plug in one module and then we do double width and then we skip the other slot. And then because I think the density need for the accelerator is not the same as the flash side. Yeah. Yeah. I think I should like delete the 9.5 or 25 here. I think the message here is to whatever the thickness of the flash, for example, right? We could accommodate like the same, or we double the thickness. Yeah. That's right. Right. Yeah. So there's no. I think it's flexible for the accelerator, depending on how many you want to plug into the same system. You mean the interconnect in between accelerator module, right? I think for training, we are doing that already. For inference, I think Pcie is good enough to have the communication between. That only happens when you have a bigger model that one accelerator module cannot hold the model. Then you will have the communication like that. And Pcie peer-to-peer is good enough. Yeah. Yeah. So far, there's no need to build interconnection between, since the it's not like training. Training model is a lot bigger. Yeah. Yeah. Yeah.
And
yeah, so NVIDIA NVLink is a great example here, right? And then earlier this year, so we had the OCP accelerator module already released, and then a lot of company already aligned. Even NVIDIA, they made an OEM, like NVIDIA OEM, right? And AMD, Intel, Habana. So those company are making the OEM, which is they have a lot, like I think we built a 8x16. A single module, we have 8x16. So 1x16 for Pcie, the rest of the 7x16 are reserved for the interconnection. So yeah, those are very high bandwidth interconnection. Yeah.
And one more thing on the width. So the 9.5 and the 25 are simply, that's where we're at today with E1. So whatever we come up with here, Whitney and I spoke last week that we'll try to keep things common. For building slots, it really is a PCI Express link. Keep some commonality there. So yeah, I agree. Well, we can delete that and just say thin and thick. How about that?
Yeah, yeah. It's purely depending on the module power. Yeah. Right. Any other question? Thank you.
One question. So for by 8 versus by 4, is there an ability to break up that model so that you can span 2 by 4s, for example, instead of 1 by 8, or is there an inherent advantage of by 8 specifically?
Good question. So it's really depending on the system design. I think when we are designing the system and then like what kind of module you are plugged in, right? We probably already have an idea that is by 4 by 8. And of course, the by 8 slot you can plug in a by 4. Again, the density, since the acceleration will also like need a lot of resource like network bandwidth, right? And then I mentioned about the compute is not a problem here. We have accelerator and then memory bandwidth, memory capacity. The other important resource is the networking resource. And then depending on like normally, for example, our system have a 100 gig NIC here, right? And I think we have a bottleneck there that we are not be able to plug in many devices there. So the density, I think, is not that intense, like flash, whatever. We can have like tons of devices there. So back to your question, yes, if it's a by 4, we plug in the by 4, we may waste the other by 4, or we will think not some other way to utilize that by 4. I hope I answered your question.
That makes sense.
So the chassis may be designed for accelerator only, or it could be combined accelerator and storage all together. If you use that both into the one box, then I think SSD need to follow new form factor you are just defining or describing here. So I'm just want to make sure whether your intention is to combine multiple media or accelerator into one box and then using the same the form factor at the same time. That means SSD also need to consider the kind of new form factor kind of thing.
Okay, so the purpose is design like one hardware system, right? And then we can change the bond to configure this as a flash system, or we have the same system plug in the accelerator, then this is the accelerator system. And so when you say like to design the flash, I don't think this is a problem for us. So for example, if this is the same motherboard, right? We put it in the 1U and then we put E1S there. That will be a flash system, right? And then we use the same motherboard and then put in a 2U form, and then plug in the accelerator. Then that's a 2U system. And then we don't need to redesign the hardware system. I mean the motherboard.
Right. The slot should be designed for this form factor or the E1.S or E1.long or something for flash. So I think the hardware design or mechanical design need to be predefined at the beginning. How many the E1.A or E1.S should be accommodated within the chassis of FLIS or something like that, right?
Yes.
That
mechanical design need to adjust a little bit.
So my concern here is that may give inflexibility into the mechanical design because they need to define how many drives for the E1.A should be accommodated into the chassis, right? Maybe hard at the beginning to design the chassis. It takes longer time to define many of them.
Yeah, so like with E3, we made it exactly like that, modular, so you could mix any amount of thins or thicks that you need. So if you're going to do compute, you need to do more thick. Your mechanical design can still support that. All you do is swap out your backplane.
Right.
So at least all your mechanicals are leveraged. And I think that's what we'd want to target here, so we don't go create yet another form factor that's not compatible with, if it's a 2U system, then it would make a lot of sense to make that an E3 capable form factor. And if you need a thicker thing that's there, then to go build off of that modularity. But I think, we definitely don't want to go create yet another new form factor.
So that would have worked if E3 and E1 kept the same thicknesses. So the problem is, let's say build
same widths or thickness.
Sorry?
Same widths or thicknesses?
I'm going to use thicknesses instead of width. I've been correct.
Okay.
So thicknesses, because it's not the same, you kind of broke that.
Well, yeah, but if you're going to do it 2U,
see, that's the key.
Then you're not going to do an E1S anyway, right?
Why not? So let's say you built a motherboard, to Whitney's point. Let's say you built, let's call it an expansion board, whether it's a motherboard. Let's say it has 16 E1S slots of whatever width. You take that same, whether it's a PCI Express expansion board or motherboard, put it in a 2U, and now you just change whatever carrier that's plugging into a slot. The same origin, it just grows taller. So you could go the height of an E3, yes.
Right.
But you can't use the E3 because it's a different depth and a different thickness. So with this concept, you have some flexibility. So, for example, on the far right, let's say you had a 2U box. You had something underneath, OCP NIC. Maybe that PCI Express expansion board is sitting on top. It's all about the depth and then freedom on the height. The depth you have to keep fixed, and then the thickness you have to keep fixed if you want to reuse it without doing brand new mechanicals.
You've got three different...
Well, I think the depth, it depends on if you start with a deeper profile. I mean, you're right. If you have a deep profile and you need to put in something that's deeper, that won't work. But you can always put in something that's shorter.
You could go shorter. But if you want to consume E1S and you want to consume accelerators in the same box, you have to constrain that depth. So you could pick the longer one and put everything else in the carrier.
Right.
But if you have an E1S and a carrier, you probably don't want to do that because you probably have that SSD used somewhere else in the platform, a different platform, for example. You don't want to remount it on yet another latch with an extension. Then you're down to an extra part you keep in a data center. So this is where I think, if we rewind time a year ago, we'd make E1 and E3 the same depth, and then we keep consistent thicknesses. So I think because that didn't happen, you're going to have these divergent paths, and the goal with E1A, at least the concept we're sharing here, is let's reduce the divergence. If it's only in the height, and it's no longer in the thickness or the depth, you can reuse a lot of what you've already done. Because if you, let's say you built a 1.5U chassis, you could put an E1S and an E1A in any slot you want. Just the height of that latch gets a little bit bigger.
One of the things that is funky about this proposal, though, is that your thick devices are not an even multiple of your thin devices.
Ignore that. That's why ignore this. So what we're defining with E1S, what we talked about in the very beginning, whatever we define as a thickness. So instead of 9.5, for argument's sake, let's say it's 15, and then let's say we agree on a 2 millimeter gap. That would mean this would be 15, and this would be 32. Or let's say this was 10 millimeters, that would be 10, and this would be 22. So you have to keep the same pitch. We have to define that.
Forget about the thickness here.
Exactly.
I think the concept is to leverage the single width or double width of whatever the E1S.
Yeah, that's exactly what we did in E3.
And you keep consistent depth with E1, and that's the problem.
The problem now is that
I would argue E1 didn't keep consistent depth with kind of
either one, to be fair, from seeing from the outside.
But my bigger point is the Gen Z scalable form factor, it does all this already. Everything is scalable off one another. You can go up or down, X, Y, Z dimension. So again, before we go create something else, let's go look at that and see if that would suffice to do this, because that'll allow you to have a 1U optimized, smaller form factor, different thicknesses. It's all the same depth, and it scales off of different dimensions. You can make it twice as deep, 3 times as deep.
So we say the Gen Z form factor, is that the
scalable form factor and the mechanical?
So E3 is a subset of
the
Gen Z.
So we could make E1 align with E3 so that
correct.
So I think I did this out with John Norton a year ago, and but Lenovo weren't up for it or something like that.
Yeah, originally that's the way it worked.
That would have been
Lenovo wasn't up for it for a reason, right? So E1.S does not have enough. I mean, if you talk to all the drive manufacturers, E1.S does not have enough space on it if you go to 100 millimeters. And the main reason we went to 112 or 111.5 is to give enough space to fit the number of packages of flash that you need. So, and the drive, so instead of matching U.2, which is 100 millimeters, just the legacy U.2, what it happens to be, then we grew the card to make it useful, to put the right amount of flash on it. So the E1.S can get smaller, which is what it would have to do to get to the E3.S. E3S could go to 111.5, and it would fit in the same depth as a 3.5-inch drive does today. So the mechanicals, in a lot of cases, would still work. And the tray already that you mount on a U.2N today, then it takes up a lot of space, and there's space there that could be consumed back into the card depth.
But again, we can't switch to large form factor chassis for everything, Jonathan.
Yeah.
So I think the main thing to look at is, I would just say, if you guys aren't familiar with it, go download the Gen Z scalable form factor specification. It does exactly this. E3 is a small subset of 4 form factors of that scalable XYZ dimensions. And so it was kind of a targeted, this is sort of a thing that's, let's go define it and do more work on it, but let's not. You can do, obviously, infinite with the Gen Z scalable. You can pick whatever XYZ you want, but it already takes into account all the multiples of different things. And so I think we should at least look at that if we want to say we're looking to go do something that's scalable and modular. Go take a look at that and see if that's something that will work.
My concern is for that, the ship seems to have sailed. We have a lot of E1 devices. I mean, if someone's already been designing boards, we have multiples here in the room today. Now we're asking them, can you go back and change? That the time to have aligned E1 and E3 was probably a year ago, and I agree it should have been done. So what you're proposing is exactly where we as an industry should have been. It's a mess.
Yeah.
I'm not pointing fingers. I have not seen how we got there. Either way, they are not compatible. E1S and E3, E1 and E3, they simply aren't. I mean, the depth, the width, we each went down different paths.
Well, E1's not even compatible with itself.
But E1 exists. I mean, we're looking at 4 separate E1 devices here.
Yeah, but they're all
E3
different.
devices. To be fair, I mean, good intent.
You look at thicknesses, height, and depth. There are multiple of those.
Depth at least is consistent, but you're right. Today we have 4, at least in the spec. Doesn't mean manufacturers are building that. The goal here is we should align on 1, maybe a second for boot, something that doesn't use a lot of power.
So a slightly different dimension, the height here. This really proposing 3 different heights of 31, 76, and 50. Is that what I'm seeing there? So that you can do.
I guess the message here. So 76 is the maximum we can go with 2U, and the message here, the height is, the 1U, I think the 31.5, like compatible with E1S is what we want to do, and whatever in the middle, you can plug in the system. It's really depending on the power and the thermal of the accelerator vendor, right? And then if we are like designing a 2U box, I think they can based on whatever they can choose, which is still compatible to be in the system.
How is that? So
because you are plugging like this, right? You are plugging like vertically.
So I guess that's the piece I'm struggling with.
Yeah.
Because I got a 76 millimeter height, and I got a 50 millimeter height, and I got a 31.5 millimeter height. But you're saying that 76, I think, changed the orientation?
No, the 76, for example, if people want to save whatever, even like the PCB cost, for example, right? They said, oh, we don't want a 76, we go 70. Is that okay? I think it is okay. I mean, as long as
that's another form factor.
No, so accelerator vendor gonna make the module, right? So these are commodity that people are buying, and then the accelerator vendor, when they go and design the ASIC will come with a different power. So they have the performance target and the power envelope.
I'm still missing. I have to have a physical mounting.
We can certainly have a guidance here, like let people to go like a design, for example, up to 70. 6 is based on whatever power envelope, right? And then if you are targeting, for example, 30, 40 watt-ish, and then you may targeting like 50, we can give some guidance here.
Still sounds like 3 form factors.
Let me address this. So hold on. So if what Paul was saying earlier, if there was alignment between E1 and E3, that would be E3. That's your full height in a 2U to optimize space.
Right.
But because you don't have alignment, I think, but what he's saying is we need to figure out what makes sense. Is it something smaller that you can then stack, or bigger? And I agree. We may not want to go down the both. I think both would be very challenging.
That's 3. I got one that sits over an OCP slot, and one that takes the full height of a 2U, and another one that's optimized for 1U.
This will be different, like a system, right? Or different system.
Yeah, but
the system
I
with a
have
different.
so the same accelerator doesn't work in all 3 places. Right, so I end up with the same accelerator in 3 different.
Well, if you built one to this, you can put it in a carry that would go wider and maybe use more heat sink. there are options you can do, but this is where, rewind the clock, E1, E3 alignment, short, tall, middle. We would have solved this as an industry. So maybe this isn't the right approach. We're proposing this as how do we think about this? The key was, E3 and E1 are not aligned. If Whitney wants to adopt an accelerator that would fit in E1, and she wants something that's in E3, that's a different chassis. Different thicknesses.
Well, it's going to be a different, even if you did an E1, that 76 is a different form factor.
So what you're telling me now is if E1 and E3 magically align all of a sudden, E1, E3, you've solved her problem.
Right.
Well, but you still got this other one. You don't have a form factor that fits your 50 millimeter. That's still a new proposal. But
if you had this, maybe Whitney and other teams can figure out a way.
So accelerator is a different. For example, it's not accelerator they have many different accelerator vendor, right? They are building these. So if we have a guidance for them, they were built like this module.
The accelerator vendor then has, so your costs just go up because your volume just got cut, by all these different form factors.
It depends on the power envelope again. Yeah.
And tell me if I'm putting words in your mouth, but if you built something in this form factor, put it in a larger form factor with a bigger heat sink, heat pipes, same PCB, maybe just different thermal. I don't know if that's what your intent was, but that's kind of where my head went.
Yeah,
it would have been great if we had E3 alignment.
I think you could do that if you didn't sacrifice much, right? The challenge would be is if you get something that fits in 50 millimeters, are you going to sacrifice it? So would your option be like, well, I don't really want that, right? So I want something that's optimized for 76 millimeters or the full 2U because I can get 30% more performance or more, data points inferred from it. So I think the challenge with that approach is just, again, it's like with NAND. You probably wouldn't do that because it's really volumetrically inefficient. And that'd be the same concern here is you wind up with just kind of proliferating form factors potentially because you have different form factors optimized for different use cases. It's just, I guess it depends on whether that really makes it worthwhile.
I think, just jumping in here, I think everybody's agreeing, but they're looking at it from their lens. So the E3 guys would love this idea if E1 aligned with E3, and the E1 guys would love this idea if effectively it gets rid of E3 and aligns E3 with E1. And so the problem is, and okay, there's people that are out there with devices. This was discussed. I personally was involved in this discussion over a year ago with all the main players, and I did hear that the big names, not Facebook, but other very big names were wanting alignment, and it was chosen to ignore it and let Lenovo stick with as it was. So, or let the E3 guys, let Gen Z stick with it with the way they have it. So I guess the problem we've got is I think everyone would 100% agree alignment with E1 and E3. If we could walk away from this meeting saying that is great for the industry, then we need to work out which way do you go.
That's an excellent way to put it. But I would ask, has the ship sailed?
If you hit it, Intel's shipping EDSF products today.
You could say the ship has sailed. I mean, you can let the industry decide if we want, and we just go our different ways, and the ones that's wrong are going to have to change their systems in a year or two's time.
Yeah.
I think the industry as a whole is better off if we had alignment.
Oh,
with
yeah.
or without devices in the market today.
Nobody disagrees with you at all.
Okay, so you're ready to switch E3 to the E1 depth then?
No, because that breaks a whole bunch of other stuff.
Yeah.
So that's actually, that'd be my request. That would be my request is go back and check in your systems because we're retrofitting E1.S in our 2.5-inch bays. And I've measured Dell and HPE chassis and seen where I could fit. Now, obviously, you know your portfolio, right? So it's something for you guys to look at. But I think that's
and Jonathan, we've looked at that, right? Because we tried to figure out if we can just accommodate it and work out some mechanical slop and look at carriers and optimize, and it just doesn't work.
Yeah,
I mean, it's just a couple of millimeters too big.
We both came to the same conclusion. Both Dell and HP tried. We tried on our side. We could not get it to fit.
Let's talk depth real quick. So I don't have it up. I forget which one is shorter depth-wise, E1S or E3 short.
E3 is shorter.
E3 is shorter.
E3 is shorter.
No, E3 is shorter.
E3 is shorter.
Yeah.
Okay, E1S is the longer one.
Yes.
All right.
Except the long E3, the E1 will go into it.
Yeah.
Yeah.
Long, because I think a lot of us are interested in the short. Yeah. Although, actually, hold on.
Temporarily.
Because the long will push some of our chassis out. I mean, speaking for Microsoft, I don't know about others in the room, we would be flexible, and then a device of an E1S could go a little bit longer in a carrier. Puts a little more challenge for us, but it's not insurmountable. But we still have the challenge of E1S and E1L being different heights as well. So do you then say that the half height is the E1L height and E1S will fit in there? That certainly works. But I know there were some concerns, and then at least I heard the history of how E1S started, that it got a little bit shorter. How do we agree?
That's the other problem, is E1L and E1S not being the same height. That's bizarre as well.
This whole form factor mess is bizarre. I was going to put a picture up. I got several different vendors to send me all the images. I was going to put it on a slide, I think, that would break PowerPoint. I mean this should be a red flag that, hey, somewhere something went very wrong.
I actually have a slide with all of them superimposed if you want to see it.
Oh, is it Intel only, though, or is it?
No, they're generic.
Oh, good. So I took,
It's a picture of a PCI card, an M.2, an U.2, an E3, all those on top of each other, and you can kind of see what that looks like.
It's a mess. I kind of wish we did this 2 years ago.
Well, so we did. I guess the way I look at this is E1S, I think our ship is kind of sailed. I guess that's our perspective because we're selling them now. But that E1S will go into an E1L enclosure, and then you can use it for that. So those two kind of are compatible right now, right? I mean, they're different links, but you can put, I'm sorry.
How deep was E3L?
E3L.
That's a 3.5-inch hard
I
drive.
think it's like 146 or something like that.
And E1S
142
fit into an E3L.
142.
Yeah.
You said the E1.L and the E1.S are different heights, but if you take the E1.S PCB and put it in the E1.L case, now you have a solution.
Yeah.
That's something similar we wanted to do for E3, to reuse PCB for smaller capacity drives or whatnot.
Yeah. But it was too short, though, right?
Yeah, it sticks out of the E3 short.
All right, so
that's why we're looking at long to put that E1S not only in a E1L, but an E3 long. Right?
Yep.
And I guess an E3 short will go in an E3 long as well.
Yep.
Any other system people here have an opinion?
So hang on a minute. So an E1 could go into a E3 long.
Yeah.
So you could, that would give you a backwards compatibility with a caddy. And then you could reinvent a new E1 that's the same length as the E3 length, and so that you could plug a 1U E1 into the same backplane depth, and then all of these options that could be possible.
I guess my question is, if you have an E1S and an E1 long, why do you need something else? Can we just stop there?
I think we just heard dissenting opinions on that.
Yeah. Okay. I'm sorry. What was the?
What did you say?
Well, so he's saying, why do I need an E3?
Oh no. I like E3. I'm just saying we're talking about E1As and all these other things. If you have an E1S and you have an E1L, and that E1S can go in an E1L enclosure, and they both work, why do you need another 1U form factor?
Okay.
Isn't that enough? We have enough already.
And so, what do you want me to answer for you? I don't even know.
Go ahead.
Okay, now I have my kidding. So, all what he's saying here is for storage, we see E1S. Whether people like it or not is another question. We'll ignore that part of the question right now.
Good call.
And for accelerators, it's desirable to have more PCB height.
Agree, and that's why we need E3s.
But if you have a storage box and you want to put an accelerator in it to mix and match, you need an E1S with more height, and that's her intent of the picture. What that height is TBD, open, not defined here.
So I would argue
that's
that
because
the E3 kind of is that.
But that's because you're saying you're limited to a 1U. In that storage server, you're saying you're limited to a 1U height. So that'd be different than the middle picture there that shows scaling to 76.
the base board will fit in a 1U, or you can put it in a chassis with 2U mechanical.
Right.
So the 50.
But then
you're gonna have to rip.
But it's a different depth, so the connectors at a different place.
It's all about the depth. Because then you're saying that if you're going to design it deeper, then you need a much longer latch if you're building a storage box. You no longer have a little latch, you have a deeper latch. Could you? Sure. But again, you still don't have the same width. I mean, there's still other challenges. There's not alignment.
Yeah. So the accelerator is, I have some example like the package, right? And then these are whatever the current generation or the planning for the accelerator vendor. And then moving forward, they may coming out bigger ones. And then when they put a more memory channel there, and then we certainly need more memory channel. I think this is a concept to just leave the flexibility to grow up when we need a more space. So we have whatever slot already defined there and the depth defined there, and we are flexible to grow more PCB area if needed in the future. Since the power envelope, for example, the accelerator is not like a NAND flash. I'm not in this area, but accelerator, it really depends on how much compute they put there in the architecture, right? They have a different power envelope there. So that's exactly why it's hard to define like a single form factor fitting to all accelerator needs. And we need the flexibility here.
I guess I'm still missing why you can't have the E3 enclosure. And you can design your PCB whatever size you need to save space or whatever you need to do as long as you have that same card edge.
Well,
we can.
The problem is the E3 is shorter than the E1 he's already
Exactly. Yeah. If we aligned the depth, right, or the PCB length, I think E3 fit perfectly here, and then we can change the height of the
So we need to be very careful when we talk about E1s and E3s. If you don't add what length it is and what thickness, then it kind of...
So an E1 short box that can be put into a 2U chassis to accommodate a higher product, what do you plug into that? And they're saying this E1A could be that. We're saying it could be, why not just do the E3, but the length then becomes a problem because you're too short.
Unless you do the E3 long. But then the E1S will go into the E3
but you're
enclosure.
Too long.
Well, you have to design your
E3 long is longer than the E1S.
So the E3 long is certainly an option there, but what's the impact if you take the E1 short and you cut those 4 or 5 millimeters off to make it the same depth as an E?
You don't want that stupid PLP, right? We
it's 11 point.
It's 11 point.
Too much stuff on there.
So what's that impact as we see NAND getting to be gigabit
PLP
16 die pack?
Is
that really beyond the capacity that the industry
So
needs?
we're talking about putting an E1S in an E3 long enclosure. Why not just put the E3 in an E1S equivalent enclosure for that 2U chassis and just create a new frame and not a new PCB? Frames are a lot easier to do than a whole other board.
Say that
I can
again.
put an E3 in an E1S 2U high frame as easily as I can put an E1S in an adapted to E3 long frame. So my PCB stays the same. The external frame has to change, so be it. So that makes our guys that do all the extrusion molding and everything else happy, but our PCB count, our SKU count goes down.
Now you just have to worry about the width, and the E3 thick is 16.8 millimeters. So if that's one of the ones you're looking at, like as an in-between of
we got up to the 16.8. We were seeing, because that's the double thickness. For us, 12 to 15, as soon as you start going 16, now we're losing density for 1U platforms that are optimized for front surface. And this is catch-22.
But I think the sheet metal wrapper around the solution to get a taller card in a 2U but E1S equivalent length is taking an E3 and putting it in a new frame, not redesigning a new board. Keep the PCB as an E3 board. It'll fit all of your form factors with the accelerator, and just have the E3 short in an E1S, because E3 short is shorter than E1S. He's trying to fit an E1S chassis, put in a 2U height. Just make the frame fit the E3 and call the PCB done.
Yeah, Scott, the problem with that on the system side is that won't fit in our front end. Because all of our chassis, right, we'd have to go make an EDSFF specific chassis.
But you have an E3 chassis that you're going to have an E3 frame for, but it's the same
it's an
PCB.
SFF chassis. It's the same depth as our SFF chassis, and the front end, we only have the same amount of space to fit an E3 short.
Yeah.
So we can't fit an E1. We can't fit that inside of an E1S, which is longer.
For your chassis, you have an E3 short. You're doing your thing.
Right.
You're taking that PCB and putting it in a slightly elongated frame to accommodate his E1S tall.
But then it'll stick out the front of our server.
No, because you're not using that same form factor. It's only for the box he's talking about. I'm trying to avoid creating an additional PCB.
Yeah, we're saying 2U server stays on E3, but they can have leverage
for his unique form factor, where he's taking a 1U chassis and making it taller to accommodate.
Right. Well, so the problem with that is
into Paul's chassis though. So if for some reason Paul wants accelerators.
Yeah, I was going to say that's the problem, right? When
but
we say, okay, we want accelerators and we're not going to be compatible.
In his E3 frame. The Facebook frame becomes the unique one because it's a little longer to fit the E1S existing chassis that he's trying to accommodate. His E3s is an E3. Again, the PCB is the same. His frame will fit either way.
Shorten the PCB.
So I see what you're saying. Two different SKUs.
You would have.
I would have an E3 accelerator.
Yes.
Then you would take that same PCB. If you're the manufacturer, you'd go package that in an E1S chassis or frame.
Yeah, you have one PCB, an E3 short.
So slightly
PCB,
different SKU at the end.
Different frames.
Yeah.
Like you're saying, an E1S can fit an E1S.
Right. I see what you're saying. And that would work.
The PCB is the hard.
You're leveraging the PCB and the manufacturing, and then you just package it slightly different into two SKUs at the end.
So here, let me take a different poll, and this maybe is not in the room. So I like what you're saying, but here's the catch. If no one's going to put this accelerator card in an E3, then let's say the Facebook team and their vendors will be giving up 11 millimeters for a use case that doesn't exist. So you'd have to see, are there consumers for it? The answer is yes.
But
what you're saying makes a lot of sense.
We're trying to drive them to define, we're trying to define a form factor, ask them to build. So we have them build it on an E3. Does it not fit in an E3 today? Right?
Right, but if you're going to constrain the depth, so you're going to lose that 11 millimeters you would have otherwise had in this, is it worthwhile if there are no adopters in a standard E3?
I would say that we would be adopters of that. Right, so
I was going to say,
depends on how big the ASIC is. I think when you mentioned 60, 70 watts, could have big ASICs and DDR and NAND placements. There could be a lot there. I don't know that. I don't know if you want to speak to any more of that.
So we really want to have the flexibility for future cases, right? Yeah. Let me.
If you have someone that couldn't fit in a standard E3 on an accelerator based on what we have in the market today.
And I believe the E3 short stick is 35 watts.
Yeah.
That's right.
Your short stick is 40 watts.
40 watts. The height here is still 76, right? So we need a 50 something.
No, it's 76 millimeters.
But it won't fit into. We have an OCP NIC underneath. Yeah.
Well, that's unique either way. No matter what you do,
when you do that,
that becomes a unique spin-off of anything that we're trying to define here.
Yeah. Especially, if they are 20 or 30 watt, for example, 30 watt each, right? They may not need that many.
So we have a predefined 1U, it's E1 whatever. Right. We have a predefined 2U that's an E3 whatever. You're looking to do something in between, so that's custom regardless. So call it whatever you're going to call it, E1.5.
But they do have some use case like OCP NIC is under there.
Agreed.
Yeah. And then we need to accommodate that use case as well.
Yeah. But I'm just saying your E1A76 is, from what I can tell on the market, is useless if you just take an E3 and worry about the frame you put around it, less than you do about redesigning a full new PCB.
And there's option, B, C, D, whatever we haven't talked about. You take the equivalent of an E3, size, rotate it 90 degrees and put it above.
Yeah.
And then you have PCBs with cables. Maybe that's
well, that 50 millimeter, you're going to have a cable no matter what.
Yes, or a connector that can get it up there.
Yeah.
Or a orthogonal connector like the E1S currently does.
But to get it to your motherboard, you'd still have a back connector of some sort or a cable.
You're going to have to clear the back end of that OCP. So it's going to be an orthogonal connector that if you think the SI is bad on the current one, that one's going to be almost unblockable.
You'd have a PCB under, above it, and then some sort of memory connector, like a riser card.
Yeah.
On a 1U2 server, something like that.
Your best bet is flip it on its side and go up through a riser. But those MES card connectors are not changing.
Agreed. So again, same depth. If we just aligned on depth, that makes this all so much easier. Whitney would walk away happy.
Why is the OCP NIC horizontal in the first place?
Doesn't have to be.
It's
coplanar.
It's a by 16.
That way,
Yeah.
yes.
Unless you're going to do a by 16 sail connector. And then you need 2U as well.
Yeah.
Well, you could do a by 2 vertical connector on a backplane, or by 16 vertical connector on a backplane.
Then you need to go to the OCP NIC group to make the suggestion.
No, I like the NIC this way. We can do the other ones. I mean, let's keep the NIC coplanar. I think we have a lot of use cases for that. And no A is not for Anthony. Sorry.
Well, hey, you're suggesting creating all kinds of new form factors for drives. Let's do new form factors for NIC.
We already have a new form factor for NIC.
I would argue an E3,
really?
an E3 short thick is the same thing as an OCP NIC right now. Well, it's really precise, right? An E3 thick short
About the same as
is
an OCP.
about the same size as an OCP NIC 3.0 and a U.2.
Yeah.
So we've got 3 form factors for the same real estate. Why can't we consolidate that down to one? E3 short or something, right? Or long.
Yep.
For the 50 millimeter use case there, do you really see that that's an absolute requirement, that you have so many slots there that you must come up with that you don't have enough other slots in your server front and back?
Unfortunately, this is currently Facebook project. Like we do have a use case like this, like OCP.
I know there's a use case. The question is more about, is it a big enough use case to go create a new form factor, right? I mean, we all know that there's a certain amount of space on our bezel. We could take up every square millimeter. But do you really need to, is more of the question, to go create, because that will be, no matter what we come out of this with alignment, that will be another new form factor.
Yeah. So why I'm collecting the requirements like from different accelerator vendor, right? I think majority of them, since Facebook already contribute the dual M.2 spec, so if dual M.2 together, the width is 46 millimeter and the depth is 110. And then the current, the feedback from these accelerator vendor, the major one, right? They are all be able to fit in this like 46 by 110. Mm-hmm. So and then this is the one that people are thinking about. These are the PCB area they need, like for at least the current generation or whatever generation they are developing with.
But what does that have to do with having to place it over the OCP NIC?
So OCP NIC is just a use case that if you need the density and then OCP NIC sit underneath, and then you can still plug in whatever, keep your density there.
So maybe to re-ask that question. So in this case, above the OCP NIC, if we rotated 90 degrees, so then they're horizontal, and it was an E3-like device.
Then we have to stack multiple like this, right? And I don't know the signal integrity for the highest one.
You'd have PCB and extension cable, kind of what Bill was mentioning earlier today. So you would have a cable assembly most likely, or PCB and a backplane.
The serviceability, I doubt the serviceability is like, I believe
have better SI than what you're proposing.
The SI, I would argue for like serviceability and also the cost, like PCB, whatever cable PCB connector cost, right? Like versus you are just plugging and then service like very easily, like U1S.
It just seems like the space above the OCP NIC, you might be able to address that with devices that already exist, and instead of bifurcating the market even more with yet another form factor. If you said, hey, we can go turn those horizontal, we can deal with that with another existing form factor. We can still put accelerators in that space, but we don't have to create yet another new form factor and bifurcate the market even more.
I would say for accelerator work, there's no like a single form factor can fulfill the growth there. I've seen like people are talking. I mean, for example, NVIDIA T4 is already 70 watt, right? And people are thinking about like a different power envelope. It's really hard to say like for accelerator work we have a single one. That's why I say like a 50 by 111 here can fulfill the current generation or whatever the generation they are working with. And then in the future, we don't know. For example, people may thinking we need a more memory, and then we need a more area to put more memory there. Here, from my understanding that we can put more 4 memory channel there. What if we need more like a 6 or 8 memory channel? Then we need to grow the PCB area. That will be a different one. But in this case, we don't want to change for example, the PCB design, the baseboard design, the motherboard design. We can just grow the height here, and then we can still fit in. For example, tomorrow there will be a new accelerator vendor, right? Stop or whatever. They come our whatever solution.
If you put that device above the OCP NIC, you're definitely going to change your baseboard design.
So that's
absolutely.
So this is the design we want to currently keep, the same as our flash system.
This is maybe specific to their design. Yeah. So I don't know if you guys have anything you're able to share later, but let's pause for 1 second. So we're at 4:45. So we've gone through this a lot. I think we've highlighted back to the beginning. We've had these form factors, divergence. If we had convergence, we would have had better options for Whitney. All right. So with 15 minutes left, is there anything else we should be covering? I think we talked about mailing list, convergence on thermal at least, so we can start modeling things. We can align the thicknesses. Maybe we take an offline, mailing list as well to talk about accelerators. Do we see convergence? Scott and team have had some ideas on, using the 100 millimeter depth. We can certainly go explore that. So.
At least for the E1.S width, how do you want to handle that? Like with the OCP poll?
Yeah.
So this part here, even. Trying to find the thickness.
Yeah.
So this way, I think before we start doing this with a poll, I would argue we need to solve the thermal methodology, because the thermal simulation is going to drive the answer here. So I say maybe I'll kick off that thread, make sure that everyone here is on the email list so you'll see it. Let's try it. I mean, maybe we have a couple calls.
We didn't cover the Intel data, but 9.5 millimeter and 20 watts seemed okay for up to 8 terabytes for us on field. I mean, and we, again, lots more data needed, but
about 1.75.
Are you talking about the FMS data or using the multiple bodies?
No, we had simulated data.
Simulated data that's based on correlated data models, right? So it's pretty accurate.
So certainly share that to the mailing list. High-level bullets. This is what you've done. This is what you see. I think that'll help drive what we're doing here. But that's more than just Intel's going to make sure everybody's selling.
Just are you saying though that thermals will be the driver that would select where that thickness ought to be?
That's my take, unless someone sees this differently. I mean, I think if we know the mechanical height, if we say it's E1S, we're only thinking about thickness now, forward-looking. So if we're going to grow outside of the 9.5 in the spec today, that forces you to 25 in the spec. So I think there's some gaps in the spec.
That was part of my question about the capacity. Like the 8 and the 16 terabyte drive have pretty different power profiles. That targeting one for 3 years from now is completely different.
Exactly. But I think if we're designing a design right now, and then a year and a half, you go, actually, we can't put a 16 terabyte in there. Then you go into double width, then you're in something incredibly wide, and then you're back close to that 25. Ideally, we should go a few gens out before we have to go to these double thicknesses. We will change our terminology. Try to get that through. So, do we agree? We'll use the thermal to help drive that?
Yes.
Any dissent? No. Perfect. All right. Oh, Anthony. So cool.
Did I get it on time?
Sorry?
Did I get my hand up in time?
You did.
Going.
Registered as one. Did I have to explain it?
No, I mean, the only thing I want to make sure to modulate this is with front density, like how many you can actually put in the front.
That's the key. We want it to be the smallest, reasonable.
Exactly.
We don't want to go to like a 50 millimeter wide thick device. And yes, you can cool anything until
exactly, because I mean the thicker, it's just because at some point that modulation starts dropping off drives in the front, and then that will start reducing the number of attachments.
That's what we were showing in the first track. Is like, all right, there's a diminishing rate of returns. You get a lot of thermal benefit, then you get to that 30 watt range. We think that's somewhere in the 12 to 15 millimeter. Gives you plenty of margin.
Take a pretty big hit in the number of devices you can support and the total system capacity.
Which is why we want it to be the narrowest possible that's going to work there.
And have you considered making the devices longer, somewhere in between E1.S and E1.L length? I know I hate bringing it up because I
was intentionally not bringing that up, because if I was going to do that, I would say, all right, then why is E1S shorter than one
Well,
L.
so E1.S originally, right, we wanted to maintain that M.2 use case where you put it on carrier cards and it was small and flexible, but if you're talking about putting it in an enclosure, it's a different. You're working with different attributes.
So let's ask it slightly differently. So from our side, we can build a system and a chassis fairly easily, but there are many device creators here. Raise your hand if you would like to redesign your device and reconsider the form factor, making it wider. Oh, come on.
Well, like you said, there's an evolution. We could have a next Rev 2.0 V1.S.
Yeah, but if you build a platform now and you come out with a new device, we don't want to redesign our platform. We need to decide that now.
Well, but we, John, and he's not speaking up now, but E1,
I'll build it.
But think about like U.2.
I hate the idea too.
SFF and LFF has been for decades.
there are people who are saying that's all they can fit in there.
Rev 1.0 trying to do flash specific.
That is a real
data center.
It doesn't go away.
Density type stuff. We didn't get it right.
No, I don't think we got it right.
How many revs of 2.5 SFF and LFF
we really
back when they were first created?
But we can't deploy hundreds of thousands of machines and then no upgrade path that goes wider.
Then that becomes a problem for the guy that builds it.
Problem for us as well. So if there are 10 vendors and then only 2 want to build it and that's their way.
So Jason, one other thing I'd expand upon what Anthony said was, I mentioned it before about the number of lanes and bifurcation. If we're talking about thicknesses that are going to break some kind of binary number, I don't think that's going to work for, HPs and Dells could argue, that there could question this, but if you have bi-16s coming off of the CPU, they want to use all those lanes. So if your thickness changes and you can only support 22 instead of 24, or 23 or 24, that just doesn't work, right?
Sounds like the system designers have to push back.
Yeah.
But again, you can also adjust your gap as well. So if you need to get those extra 2. But I would argue we shouldn't make a specification off of one vendor's implementation. So if you're at 22 versus 24, my take is that's okay. If someone else wants to push back on that. I'd rather 22 that you can cool and versus 24 that your fans are going 10, 15% more. Because we don't care about sheer number of slots, we care about TCO. I think at the end of the day, every customer cares about TCO. Some know how to measure it, some don't. Maybe it's the cost of the box. I have a rack with 2,000 slots versus one that has 900.
HPC cares less about that, right? They care about performance, flat out pure performance, right? And so it's not all, I probably shouldn't say this, but, there's enterprise, there's cloud, there's HPC, there's hyperconverged. There's a whole bunch of different market segments that these guys that are vendors have to sell into. And they have to make their drive such that it fits all of those, not just cloud or one.
I think we'll never hit 100%. I don't think we'll ever hit 100% of getting what people want. But if we can get the vast
But if we change a spec such that it doesn't fit 24 and it only fits 23, I see that as a fail.
What do we fit today with 25? There you go. You fit less.
Yeah, but look how many ports you have coming off the CPU too. Right?
It doesn't have to be a CPU. PCI Express switches are readily available. And maybe a certain CPU vendor can bifurcate down.
There's a direct attach, there's switch architectures, there's yada yada.
All right, we're near the end of time. Any other presentation slides that anybody wants to share?
Were we going to do Anthony's? Not Anthony's, Z's.
No, so Z was going over the mailing list. That was the connectors.
Okay.
So the intent there was probably less of debate. I think we're all fairly well aligned on that, unless Z has wants to share it specifically here. If there's any contribution you can.
The one thing I do see there is an opportunity to maybe have a different E1.S version between PCIe 4.0 and 5.0. There may be platform refresh as well as a drive cycle refresh, where we can have an opportunity to change the spec drastically. But
hi, I'm from Samsung. This is Peter. Yeah, we just quickly let you guys know we have NF1. Basically, the size is 30.5 by 11 millimeter, and then 16 watt and 16 terabyte. And basically, from Samsung point of view, we think all of the form factor all have their benefit and they all have their niche. So from Samsung, we like to support all of the form factor as long as customer need. Yeah, and this is from the Samsung point of view. Yeah, very quick and short.
Okay. Thank you. All right, connectors. Do we want to talk about connectors at all, or are we good?
I'm okay.
Good? All right. So I think what we may hear is there may be a request for orthogonal by 8s or better ways to do connectors with better loss budgets. Bill threw out a challenge, you get half a dB. Thanks, what Bill
said. And if you really concern the loss on the connector, we also can attach the cable to the orthogonal connector. So you don't need to have a separate cable, then backplane, then the connector. You just have one piece cable connector.
So I'll tell you from the hyperscale side, we really don't want cables. We're looking for really solid connectors. They're orthogonal. That's certainly we prefer. That's why we're using, the orthogonal connector today. We really don't want cables in our boxes.
Yeah, I'm not
server
sure.
vendors have different challenges they have to, work around. But for us, we definitely want direct attach.
Yeah, I'm addressing build concern.
All right, any last minute questions? I think we all have an action to go back. Thermals, and we'll talk about widths. And we can also open the can of worms onto what does this form factor look like if we really want to go down there, but I don't know if the appetite's there. Anyone else? Going once? Going twice? All right. Thank you, everybody. Let's use the mailing list. Please make sure you're signed up. Hopefully we'll see some traction on this here. And again, I think there was a question, how do we solve this and when? Let's try to figure this out by end of this calendar year. A lot of us have products in flight. We have a window of opportunity to fix this, so we need to know now. All right. Thank you, everyone.
Thank you.